Imagine that tonight, as the world around you slowly powers down, you carry with you a question that no human being could have asked until barely 30 years ago. A question so vast that simply forming it in your mind changes the way you look at the sky. What if out there, beyond everything you can see with the naked eye, there are worlds where iron doesn't lie beneath the ground, but falls from the sky? Worlds where the oceans aren't made of water, but of molten rock that glows in the dark? Worlds where two suns set at the same time, painting the horizon in two different colors, while the wind drives crystals of glass at 8,000 miles per hour? Those worlds exist. Not in a writer's imagination. Not on a movie screen. They exist for real, confirmed by actual telescopes, calculated by actual scientists, orbiting actual stars at distances that take light years to cross. Tonight, you're going to visit them. One by one, slowly, without hurry. Because the universe has no hurry. And tonight, neither do you. Before we begin, I want to acknowledge something. If you're here tonight, it's because part of you needs to rest, and another part of you doesn't want to do it in silence. You want your mind to have something beautiful to hold on to while the day dissolves. That's exactly why you're here, and that's exactly what we're going to do together. It doesn't matter how loud your day was. It doesn't matter how many screens you stared at, how many decisions you made, how many conversations you had. Here, time scales to cosmic levels, and those sounds disappear. Here, we talk about worlds that take years to receive the light of their suns. Planets that have been spinning in perfect solitude for billions of years. Next to them, any worry from the day loses its scale. It becomes small, manageable, and finally, irrelevant. Before we go any further, I'd love to know, where are you listening from tonight? Your city, your country, the corner of the planet from which you're choosing to travel into space before you close your eyes. Leave it in the comments. It's one of my favorite things about this channel, knowing that somewhere in the world, at some hour of the night, someone is looking at the same stars from a different angle. Now, if you're comfortable, if the light is low and the day no longer feels heavy, let's begin. One small thing before we go too far. If these kinds of journeys help you rest, consider subscribing to the channel, so the next time you need this space, you'll know exactly where to find it. No more interruptions. The cosmos is waiting. For most of human history, the question of whether planets existed beyond our solar system was purely philosophical. The ancient Greeks debated it carefully, divided between those who accepted the possibility of multiple worlds and those who rejected it as incompatible with the idea of a perfectly ordered, finite cosmos. Medieval philosophers considered it with even greater caution, knowing that claiming too much could cost them more than just their reputation. Giordano Bruno was burned at the stake in Rome in the year 1600. Not solely for claiming that other planets existed, but in part for insisting that the universe was infinite and filled with inhabited worlds, each with its own sun, its own sky, its own possible creatures. His fate was a stark warning about the price of ideas too large for their time. And yet the question didn't die with him. It remained alive, dormant, in the background of every astronomical observation of the centuries that followed. Every time a telescope pointed toward a distant star, somewhere in the observer's mind lived the quiet possibility, is there anything orbiting that? Is there a planet out there, invisible to us, turning in the dark? Or are we alone, on the only island of rock and water the cosmos has produced in all its billions of years? The first real answer came in 1992, and it came from an unexpected place. Alexander Wolszczyn, a Polish astronomer working at the Arecibo Observatory in Puerto Rico, and Dale Frail, his collaborator, announced the discovery of two objects in orbit around a pulsar, the ultra-dense remnant of a massive star that had died in a supernova explosion. A pulsar is a neutron star that spins at extraordinary speeds, sending beams of radio radiation into space with the regularity of an atomic clock. This particular one, designated PSR 1257+12, rotated on its own axis more than 160 times per second. It was one of the most violent and lethal objects in the known universe, a body the size of a city but with more mass than the sun, bathing everything around it in radiation capable of disintegrating ordinary matter in fractions of a second. And orbiting that infernal object, Wolszczyn and Frail found two bodies with masses comparable to planets. They detected them cleverly. Pulsars are extraordinarily precise clocks, sending their radio pulses at intervals so regular that any small perturbation in those intervals can be detected with the right instruments. If something is orbiting a pulsar, that something pulls on the pulsar with its gravity, making the neutron star move slightly back and forth around the center of mass of the system. That movement very slightly alters the arrival time of the pulses at the detector on Earth. By measuring those variations with extreme chronometric precision, one can infer the presence of orbiting objects, estimate their approximate masses, and calculate their orbital periods. The two worlds of PSR 1257+12 were not exactly the kind of planets that human imagination had dreamed of when it thought about other worlds. They orbited one of the most lethal objects in the known universe. There was no possibility of life, no stable atmospheres, no quiet cycles of day and night. The pulsar's radiation would sterilize any organic chemistry instantly. But they were planets. They were real. And their mere existence changed everything. It meant that planets were not the exclusive property of our peaceful solar system, and that they could form, or survive, in environments that no theory of planetary formation had anticipated. If a planet could exist around a pulsar that had survived the catastrophic explosion of a supernova, could they exist around any kind of star? The answer that the next decade would provide was a resounding yes. In October of 1995, Michel Mayor and Didier Queloz, astronomers from the Geneva Observatory working with the telescope at the Haute-Provence Observatory in southern France, announced the discovery of a planet orbiting 51 Pegasi, a star similar to our Sun located about 50 light-years away in the constellation Pegasus. The planet, designated 51 Pegasi b, had approximately half the mass of Jupiter and orbited its star in just 4 Earth days. For comparison, Mercury, the innermost planet of our solar system, takes 88 days to complete one orbit around the Sun. Jupiter takes nearly 12 years. For days meant this planet was absurdly close to its star. Mayor and Queloz detected 51 Pegasi b using the radial velocity method, which exploits the Doppler effect. The physical principle is the same one that makes an ambulance siren change pitch as the vehicle approaches and then passes you. A planet in orbit doesn't just circle its star, it also pulls on it gravitationally, making the star wobble slightly around the common center of mass of the system. When the star moves toward us in that wobble, the light it emits is compressed toward shorter wavelengths, a blue shift. When it moves away, the light stretches toward longer wavelengths, a redshift. By measuring those wavelength shifts with high-precision spectrographs, one can calculate the speed of the star's wobble, and from that speed derive the minimum mass of the planet causing it in the period of its orbit. The discovery was met with initial disbelief in the astronomical community, not because the technique was questionable, but because the results seemed to violate the theory of planetary formation. Giant gas planets cannot form close to their star. For a massive gas planet to build itself, it first needs to accumulate a solid core of several Earth masses, composed of ice, rock, and metals, and that can only happen in the cold outer regions of the protoplanetary disk, beyond the snow line, the distance from the star where water and other molecules can freeze and contribute to the growth of the embryonic core. Close to a young, hot star, heat and radiation evaporate those materials before they can accumulate. The solution that theorists adopted was planetary migration. The planet must have formed far out and then, interacting with the remnant gas of the protoplanetary disk, lost angular momentum and spiraled inward until it became trapped in that close orbit once the disk dissipated. Mayer and Kulo received the Nobel Prize in Physics in 2019 for this work. The true revolution in exoplanet detection came with the launch of the Kepler Space Telescope in 2009. Unlike the radial velocity method, which requires high-precision spectroscopic measurements that are difficult to apply to faint or distant stars, Kepler's transit method was more direct. When a planet passes in front of its star from our perspective, it blocks a fraction of the star's light proportional to the square of the ratio of their radii. For a Jupiter-sized planet in front of a Sun-sized star, that fraction is about 1%. For an Earth-sized planet in front of a Sun-sized star, it's about 1 in 10,000. Both are detectable with the right instruments, provided the photometric precision is sufficient. Kepler simultaneously observed 150,000 stars for 4 continuous years before a gyroscope failure changed its mission, and then continued as the K2 mission for several more years. During its operational lifetime, it confirmed more than 2,700 exoplanets and left a catalog of thousands of additional candidates. Its successor, TESS, the Transiting Exoplanet Survey satellite, launched in 2018, expanded the search to the brightest and nearest stars, making TESS-confirmed planets more accessible for follow-up characterization. Together, Kepler and TESS have brought the number of confirmed exoplanets past 5,000. 5,000 worlds different from ours, each with its own atmosphere, its own temperature, its own formation history. The statistical implication of those numbers is staggering. When astronomers correct the catalog for detection biases, the fact that current methods are more sensitive to large planets in short orbits than to small planets in long orbits, the statistical models point to an average of at least 1 planet per star in the galaxy. In a galaxy of 200 to 400 billion stars, that means hundreds of billions of planets in the Milky Way alone. And the Milky Way is one of roughly 2 trillion galaxies in the observable universe. The number of planets in the observable universe exceeds any name our culture has assigned to large numbers. The age of exoplanets is not just a story of technical discovery. It is a story of radical perspective. Every confirmed planet is a reminder that Earth is not the template. It is not the model to which other planets aspire. It is one among an uncountable multitude, many of them so different from here that they challenge the conceptual frameworks we use to try to understand them. Tonight we are going to visit the strangest ones. Worlds where the known laws of physics produce landscapes and climates that no human being has ever imagined with sufficient accuracy. Detection methods for exoplanets continue to improve and diversify. Alongside radial velocity and transits, astronomers use gravitational microlensing, the effect of a star's gravity acting as a lens to amplify the light of a more distant background star, potentially revealing the presence of planets around the lensing star, to detect planets at great distances across the galaxy, including planets orbiting very faint stars or ones too far away for transits or radial velocity. Microlensing has revealed that Earth-mass planets are extremely common in the galaxy, even in regions far from the Sun that other methods cannot probe. Direct imaging, photographing a planet directly, separating its faint light from the bright light of its star, is the most technically challenging method but also the most visually striking. It requires extremely advanced adaptive optics systems that correct in real time for atmospheric distortions, and coronagraphy techniques that block the direct light of the star without blocking the planets. Although today it only works successfully for young, massive planets that glow with their own formation heat in orbit at large distances from nearby stars, direct imaging is the future the astronomical community is building toward. The Nancy Roman Space Telescope will include a coronagraph designed for direct imaging of cold Jupiters. And on the more distant horizon, concepts for space telescopes with star shades, floating screens separated from the telescope by tens of thousands of kilometers that block starlight with exquisite precision, promise to bring direct imaging all the way down to Earth-sized planets in the habitable zones of nearby stars. The James Webb Space Telescope, launched in December of 2021, has opened a new era in exoplanet atmosphere characterization. With its 6.5-meter primary mirror and instruments optimized for the infrared, wavelengths at which molecules like water, carbon dioxide, methane, and ammonia have their most characteristic spectral signatures, Webb can determine the chemical composition of exoplanet atmospheres with a sensitivity that previous telescopes could not approach. In its first 2 years of operation, it has produced atmospheric spectra of dozens of exoplanets, confirmed the presence of carbon dioxide and water vapor in hot Jupiter atmospheres with unprecedented clarity, and has begun addressing the characterization of terrestrial-sized planets in the habitable zones of nearby red dwarf stars, the deepest question of all. Breathe slowly. The galaxy has time. And tonight, so do you. When the first exoplanet catalogs began to grow in the 1990s and early 2000s, astronomers noticed a bewildering statistical paradox. The type of planet easiest to detect with the radial velocity method was, for purely technical reasons and not as any reflection of cosmic reality, the planet that pulled most strongly on its star. And the ones that pulled hardest were the most massive. And the most massive ones that pulled hardest were the ones orbiting closest. So the first catalogs were systematically biased toward one particular kind of world, massive gas giants orbiting at ridiculously short distances from their stars. A kind of world that, according to all existing planetary formation theory, should not have been where it was. These worlds were called hot Jupiters, and the name does perfect justice to their nature. They are like Jupiter in size and composition, enormous balls of gas dominated by hydrogen and helium, with cloud layers of various compounds at different depths in the atmosphere, no discernible solid surface, and solid or semi-solid cores buried under thousands of miles of high-pressure gaseous material. but the temperature they experience has nothing to do with Jupiter. The temperature in Jupiter's cloud layer hovers around -145 degrees Celsius. The average temperature in the atmosphere of a typical hot Jupiter ranges from 1,000 to 4,000 degrees Celsius, depending on the mass of the star, the orbital distance, and the specific atmospheric composition of the planet. The existence of hot Jupiters immediately posed a deep challenge to planetary formation models. The protoplanetary disk theory, the model describing how planets form from the disk of gas and dust surrounding a young star in the first millions of years of its life, was explicit. Giant gas planets cannot form close to the star. For a massive gas planet to form, it first needs to build a solid core of roughly 10 to 15 Earth masses, composed of ice, silicates, and metals. Only a core of that mass can generate enough gravity to rapidly capture hydrogen and helium from the surrounding disk and grow to the masses observed in gas giants. And that solid core can only grow in the cold outer regions of the disk, beyond the snow line, the distance from the star where water and other volatile compounds freeze and contribute to the mass of growing planetesimals. The solution theorists developed, and which is now the standard model for explaining hot Jupiters, is planetary migration. The fundamental idea is that planets do not necessarily stay in the orbits where they form. A gas giant that forms in the outer regions of the disk can interact gravitationally with the remnant gas of the disk in ways that cause it to gradually lose angular momentum. This process, called Type II migration, occurs when the planet is massive enough to open a gap in the disk, expelling gas from the disk near its orbit, and then co-evolves with the disk, which drags the planet inward as the disk itself accretes toward the star. The planet spirals inward during the first millions of years of the system's life, when the disk is still present, and halts when the disk dissipates or when the planet reaches some orbital resonance that stabilizes its position. The migration rate and the final distance at which the planet settles determine what kind of hot Jupiter forms. Some migrate so deeply into the inner system that they end up in orbits of just a few days. Others stop farther out and settle in orbits of weeks. The observed distribution of orbital periods of hot Jupiters, with a prominent peak around 3 days and a tail extending toward longer periods, reflects the statistical distribution of these migration processes across thousands of different planetary systems. And the near-total absence of hot Jupiters with periods shorter than 1 day reflects the inner limit beyond which tidal forces between the planet and the star become so strong that they destroy the planet or cause it to fall into the star on cosmologically short timescales. The atmosphere of a typical hot Jupiter is stratified in layers of different composition and temperature, just like Jupiter's but taken to far greater extremes. In the deepest layers, where pressures are enormous, hydrogen can exist in a metallic state, one where electrons are freed from their atoms and the material conducts electricity like a metal, generating the planet's magnetic field. Higher up, the temperature drops enough for clouds to form. But these clouds are not made of water or ammonia like those of Jupiter and Saturn. In the most extreme hot Jupiters, clouds are composed of silicates, essentially droplets of molten sand floating in the atmosphere, iron oxides, zinc sulfides, or even more exotic titanium compounds. Clouds of molten rock, suspended in the atmosphere of a planet, illuminated by the blazing light of a star too close for comfort. One of the most intriguing phenomena associated with hot Jupiters with tidal locking, which is most of them, because proximity to the star drives synchronization efficiently over millions of years, is the extreme dichotomy between the dayside and nightside hemispheres. The dayside is permanently bathed in stellar radiation and reaches temperatures of thousands of degrees. The nightside, in perpetual darkness, is hundreds or thousands of degrees cooler, though still incandescent by any terrestrial comparison. The temperature difference between the two hemispheres drives the fastest planetary winds known, winds blowing from dayside to nightside at speeds of thousands to tens of thousands of kilometers per hour, carrying heat, gas, and condensed particles from one hemisphere to the other in a continuous cycle. These winds are the agents of exoplanetary weather. They determine whether silicate clouds form mainly at the terminator, the line between day and night, or deeper on the night side. They transport vaporized metals from the hot side to the cool side where they condense. They are responsible for the fact that in some hot Jupiters, the temperature difference between the two hemispheres is smaller than expected, signaling efficient redistribution, while in others the difference is enormous, signaling that circulation is less efficient or blocked by some dynamic structure in the atmosphere. The phase curve method, measuring the variation in the brightness of the planet-star system throughout the planet's complete orbit, not just during transit and secondary eclipse but at all viewing angles, has allowed astronomers to build temperature maps of several hot Jupiters. These maps show that the hottest point on the planet is not always at the exact center of the dayside hemisphere, where it would receive maximum stellar radiation, but is often shifted eastward, in the direction of the prevailing wind flow. This is because the winds transport the hot material several degrees past the subsolar point before it has time to radiate its energy into space. The offset of the hot spot is a direct signature of the planet's atmospheric dynamics and has been one of the most robust results in exoplanet atmosphere characterization. The existence of hot Jupiters also has implications for understanding our own solar system. When the first hot Jupiter was discovered, an uncomfortable question arose: could the same thing have happened here? Could Jupiter have migrated inward at some point in the solar system's early history? Numerical simulations of the primitive solar system suggest yes, that Jupiter migrated inward for a time, before the formation of Saturn and the orbital resonance between the two giants reversed the migration and pushed Jupiter back outward. This episode, known as the Grand Tack, would have swept material from the inner asteroid belt inward, possibly delivering water and organic materials to the inner planets including Earth. Without that moderate migration history, Earth might be a very different world. The distribution of hot Jupiters among solar neighborhood stars, roughly 1% of Sun-like stars appear to have one, has also raised questions about why our own system lacks one. The most recent statistical studies suggest that systems with hot Jupiters are probably more disruptive. The giant's inward migration disturbs the orbits of inner planets in ways that hinder the formation of stable terrestrial worlds in the habitable zone. The fact that our solar system has terrestrial planets in the habitable zone may be related to the fact that we don't have a hot Jupiter. We are, perhaps, beneficiaries of a more moderate migration history that preserved room for the inner worlds. Another intriguing phenomenon associated with hot Jupiters is atmospheric evaporation. In the upper atmospheric layers, where pressure is low and temperature can reach thousands to tens of thousands of degrees from the absorption of ultraviolet light and X-rays from the nearby star, gas can reach the planet's escape velocity and bleed into space. The planet emits a tail of ionized gas flowing outward, away from the star, similar to the ion tail of a comet. This process has been observed directly in several hot Jupiters through the detection of absorption in the ultraviolet hydrogen line. The hydrogen escaping from the planet's upper atmosphere forms an extended cloud around and behind the planet, larger than the planet itself, and that cloud absorbs part of the starlight during the transit in a detectable way. The rate of mass loss through evaporation varies enormously among different hot Jupiters and depends on the intensity of the star's ultraviolet radiation, the mass and radius of the planet, and the composition and structure of its atmosphere. For the most massive hot Jupiters, evaporation is a marginal process that does not significantly affect the planet's total mass over the lifetime of the stellar system. But for less massive planets, the so-called hot Neptunes and sub-Saturnians, evaporation can be efficient enough to strip the planet of its entire gaseous envelope over timescales of 1 to several billion years, leaving only the bare solid core behind. This process may explain the so-called hot Neptune desert, the striking scarcity of intermediate-sized planets in very short orbits, which models predict as a consequence of preferential evaporation that removes the intermediate planets from the catalog, leaving only the very large or the very small. Among all known hot Jupiters, there is one that has captured the imagination of astronomers and the public alike, not because it's the closest to its star, or the most massive, or the highest in temperature among all known examples, but because it carries the most impossible weather of all. On that planet, the temperature cycle produces a meteorological cycle so unusual, so unsettling, that its very name evokes impossible images. In that planet, on the hemisphere that always faces the dark, when the temperature falls just enough for vaporized metals to condense, they fall. Not as dust. Not as frost. They fall as rain. As droplets of liquid metal descending through the eternal night of a world that should not exist. That planet is called WASP 76b, and it is our next destination. 640 light-years away, in the constellation Pisces, there is a planet that is one of the most violently strange objects that modern astronomy has confirmed. Its name is WASP 76b. It is a hot Jupiter of notable size. It has approximately 92% of Jupiter's mass, but its radius is 44% larger. That disproportion between mass and size, smaller than Jupiter in mass but significantly larger in volume, is the signature of an atmosphere inflated and swollen by the extreme heat this planet endures. If you could see it from space, it would appear as an extraordinarily large and tenuous globe, in shades of orange and ochre with translucent cloud bands, floating in the darkness of space at a ridiculous distance from the star that illuminates it. That star is WASP 76, a star slightly larger and hotter than our Sun. WASP 76b orbits around it at a distance of just 4% of the Earth-Sun distance. In perspective, if the distance between the Earth and the Sun were a football field 100 yards long, WASP 76b would be orbiting just 4 yards from its star. At that extreme proximity, the planet completes a full orbit in just 1 day and 18 hours. And at that proximity, the tidal gravity of the star has had more than enough time, across billions of years of the system's history, to synchronize the planet's rotation with its orbital period. WASP 76b always shows the same face to its star. One hemisphere has been in an eternal day for billions of years. The other has been in a night that never ends. The amount of energy received by the illuminated hemisphere of WASP-76b is approximately 4,000 times greater than what Earth receives from the Sun. In concrete numbers, Earth receives from the Sun approximately 1,360 watts per square meter. The day side of WASP-76b receives on the order of 5 million watts per square meter. With that quantity of energy per unit area, the temperature at the layer where pressure is comparable to Earth's atmosphere, roughly 1 bar, reaches 2,400 degrees Celsius. To understand what that means in terms of which materials can exist in that environment, it helps to recall the boiling points of some metals. Iron boils at 2,862 degrees Celsius, nickel at 2,913, chromium at 2,944. At 2,400 degrees, those metals haven't fully evaporated yet, but at the temperatures reached in slightly higher atmospheric layers, where pressure is lower, iron and other metals are completely in vapor form. The iron vapor on the day side is swept along by the planetary winds, which in WASP-76b blow at estimated speeds of between 5,000 and 18,000 kilometers per hour, speeds measured indirectly through the Doppler broadening and shifting of iron spectral lines during transit observations. Those winds carry the iron vapor, along with vapors of other metals, from the hot side toward the terminator and beyond, crossing into the night side hemisphere. It is a process that occurs continuously, like a permanent planetary convective current that never stops. On the night side hemisphere, the temperature drops. Not to cold, but to approximately 1,400 degrees Celsius at pressure levels comparable to Earth's surface, still incandescent by any human standard, but more than 1,000 degrees cooler than the day side. At that temperature, gaseous iron can no longer remain in vapor phase. Condensation begins. Iron atoms cluster together, form molecules of iron oxide, then microscopic crystalline nuclei, then droplets of liquid iron that grow by accretion as more vapor condenses onto them. When the droplets are large enough for the planet's gravity to overcome the drag forces of the surrounding gas, they fall. They fall through the eternal darkness of WASP-76b's night-side hemisphere, glowing faintly like embers in the planet's residual heat, dropping toward the deeper atmospheric layers where the temperature is again high enough to evaporate them, and the cycle begins again. The observational confirmation of this cycle came in March of 2020, with the publication in the journal Nature of results from the team led by David Ehrenreich at the University of Geneva. The team used the espresso spectrograph, installed on the Very Large Telescope at the European Southern Observatory on Cerro Paranal in Chile, one of the most precise optical instruments in the world. They observed WASP-76b during several of its transits across the star, analyzing the spectrum of starlight filtering through the edge of the planet's atmosphere during the transit at two distinct moments. At the start of the transit, when the edge of the planet corresponding to the trailing terminator, the night side, is what we see first, and at the end of the transit, when we see the leading terminator, closer to the day side. The spectral signature of atomic iron was detected at both terminator edges, consistent with the presence of iron vapor being transported from the hot side to the terminator by the winds. But there was a critical difference. The iron signal was significantly stronger at the trailing edge, the night side, than at the leading edge. This asymmetry was the fingerprint of the meteorological cycle. On the night side edge, iron was more concentrated because it had accumulated there after being transported by the winds, possibly condensing partially into droplets that made it more detectable in certain atmospheric layers. It was the first direct evidence of a condensation and precipitation cycle of metals in an exoplanet. It was, in other words, the first detection of iron rain outside Earth, the first time humanity confirmed that on another world, a material synonymous for us with solidity and permanence falls from the sky like water. Subsequent observations have added more layers to the picture of WASP-76b. Studies with different instruments and at different wavelengths have detected magnesium, calcium, chromium, manganese, vanadium, and barium in the planet's atmosphere. Barium, in particular, drew great attention when it was reported in 2022, with an atomic number of 56. It is one of the heaviest elements ever detected in an exoplanetary atmosphere, and its presence in the upper layers of the planet, where heavy elements normally sink gravitationally toward the depths, requires the existence of vertical mixing mechanisms or suspended particle formation processes that are not yet fully understood. Every new observation of WASP-76b raises new questions while answering the previous ones. The James Webb Space Telescope observed WASP-76b in its first months of scientific operation, in 2022 and 23, producing the most detailed infrared spectrum ever obtained for this planet. Webb's data confirmed the presence of water vapor on the dayside hemisphere, detected signals consistent with sulfur dioxide, a byproduct of photochemical reactions driven by the star's intense ultraviolet radiation, and began building a temperature profile as a function of pressure in different atmospheric layers with unprecedented vertical resolution. Webb also detected tentative signals from silicon compounds that may be consistent with silicate clouds, though the precise interpretation of those signals continues to be analyzed. There is something deeply settling about the permanence of WASP-76b. Billions of years of iron rain in the same place. The winds always blowing in the same direction. The terminator never moving. The star always in the same location in the sky from the planet's perspective. It is a system that has reached such a complete dynamic equilibrium that it does not change on any timescale that matters. A perfect and implacable cycle that needs nothing more to continue. The astronomical context of WASP-76b adds further fascination. Its host star, WASP-76, is of spectral type F, slightly more massive, larger and hotter than our Sun type F stars are more active and ultraviolet than the Sun, irradiating WASP-76b with proportionally more ionizing radiation and contributing to both the swelling of its atmosphere and the erosion of its upper layers. The WASP-76 system may also be a visual binary. There are indications of a companion star at a large separation, WASP-76b, though physical association has not been definitively confirmed. The confirmation of the iron rain cycle in WASP-76b was a landmark not just for what it revealed about that specific planet, but for what it demonstrated methodologically. Before that study, exoplanet atmosphere characterization had focused mainly on detecting which molecules were present: water vapor, carbon dioxide, sodium, potassium, without being able to say much about how those molecules were distributed across the atmosphere or how they varied between the dayside and nightside. The technique of time-resolved transit spectroscopy, measuring the spectrum at different moments as the planet crosses in front of the star, opened the possibility of distinguishing between the trailing and leading terminator edges, and therefore detecting asymmetries in the atmospheric distribution. That iron asymmetry was the fingerprint of the meteorological cycle. The technique has since been applied to other planets with equally surprising results. Imagine that cycle, if you can. Not clouds of water. Not rain of water. Droplets of liquid iron forming in the darkness, falling through an atmosphere that glows faintly with the planet's own heat, perhaps accumulating on the night side in rivers or lakes of molten metal that never see the light of their star. The metals of the Earth are beneath our feet. On WASP 76b, some of them are above, or at least they are, on the dark half of the planet. The water cycle on Earth, evaporation, transport, condensation, precipitation, exists on WASP 76b in a nightmarish metallic version, iron evaporation, transport by supersonic winds, condensation in the darkness, precipitation of liquid metal. We know this because we learned to read the light of stars with enough precision to decode the weather on planets we will never reach. That is something worth carrying with you into the dark of sleep. Rest now. The iron rain will keep falling, as it always has. You don't have to do anything more tonight. 41 light-years away, in the constellation Cancer, there is a planet that for several years was popularly known as the Diamond Planet. The name was, as we'll see, a simplification. The reality of 55 Cancri is more complex and in some ways more disturbing than any jewel, however enormous. But the label captured something real about the nature of this world, that here, the materials we know behave in ways that no terrestrial experience can prepare us to imagine. And in the quiet of this night, that world deserves a slow and careful visit. 55 Cancri orbits a star called 55 Cancri, actually a binary star system, composed of a G-type star similar to the Sun and a smaller red dwarf orbiting it at a great distance. The primary star, 55 Cancri, is slightly smaller and cooler than our Sun but of the same general spectral type, making it a familiar and well-studied star. What orbits around it is anything but familiar. 55 Cancri has approximately twice the radius of Earth and 8 times its mass, placing it in the category astronomers call a super-Earth, a rocky planet significantly more massive and larger than ours. And it orbits its star at a distance of just 1/400th of the Earth-Sun distance, nearly 15 times closer than Mercury is to the Sun, completing a full orbit in just 17 hours and 41 minutes. That extreme proximity has consequences that go far beyond temperature. The radiation 55 Cancri receives from its star per unit of surface area is approximately 2,500 times greater than what Earth receives from the Sun. The average temperature of the planet's surface, calculated from observations with the Spitzer telescope and confirmed by Webb, is around 2,000 degrees Celsius on the illuminated side. A temperature at which iron, nickel, silicon, and most of the minerals that make up Earth's crust and mantle are completely melted. There is no solid surface on the day side of 55 Cancri. What there is instead is an ocean. An ocean of liquid rock, glowing in the darkness of space with its own luminosity, not reflected, but emitted by the incandescent rock itself. The origin of the Diamond Planet hypothesis lies in the chemical composition of its host star. Stars and their planets form from the same material, the same cloud of gas and dust in the protoplanetary disk, so a star's chemical composition provides clues about the likely composition of its planets. The star 55 Cancri has a relatively high carbon abundance compared to solar standards, and a higher carbon-to-oxygen ratio than the Sun. In the Sun and on Earth, oxygen is more abundant than carbon, and the result is chemistry dominated by silicon oxides, the silicates that form ordinary rocks. But if carbon exceeds oxygen in the formation disk, the chemistry changes radically. Instead of silicon oxides, silicon carbides form. And under the pressures that exist in the interior of a planet with 8 Earth masses, carbon can crystallize into its densest and most stable form, diamond. The model published in 2010 by researchers Nick Kumadhusudhan, Sarah Seeger and collaborators proposed that 55 Cancri E might have an interior dominated by silicon carbides and carbon, with an inner layer of graphite or diamond that could be several times more massive than the entire Earth. A diamond layer the size of several Earth planets, buried in the interior of a world whose year lasts less than 18 hours. The image captured the public's imagination in a way that few scientific hypotheses have managed. The reality, however, is more complex. Subsequent observations, especially from the Spitzer and Hubble space telescopes, and more recently from the James Webb Space Telescope, have revealed that the atmosphere of 55 Cancri E is more active and variable than a pure carbon planet model would predict. Webb, in observations published in 2023, detected spectral signals consistent with the presence of carbon dioxide and carbon monoxide in the planet's atmosphere, gases that could come from volcanic outgassing of a carbon-rich mantle, or from reactions on the surface and in the atmosphere. It also detected variability in the planet's brightness from one transit to another, suggesting that the surface and atmosphere are actively changing over time, perhaps due to massive volcanic activity, or redistribution of molten material across the surface. What emerges from all these observations is a world that lives in a state of perpetual flux. The illuminated side of 55 Cancri E is an active lava ocean, not static, but in constant motion, with convection driven by the enormous amount of heat it receives from the star. Models suggest this lava ocean could have current flows similar to Earth's water oceans, but with enormously greater energy scales and velocities. On the surface of that ocean, rock vapors, silicon dioxide, magnesium and iron oxides, sodium and potassium vapor, rise into the atmosphere and form clouds of condensed rock particles that the star's light illuminates in intense shades of orange and red. The night side of 55 Cancri E is, by contrast, dramatically cooler, but still hot by any terrestrial standard. Spitzer observations measured the night-side hemisphere temperature at approximately 1,400 degrees Celsius. That is still enough to keep many minerals molten, but cool enough that some compounds might solidify in the upper layers of the night-side atmosphere, possibly forming showers of solid particles, not of iron, as on WASP-76b, but of silicon and carbon compounds. The terminator between day and night could be a region of solidification and reabsorption of material, a boundary where lava cools and solidifies and remelts in continuous cycles. The question of whether 55 Cancri E has a permanent atmosphere or one that forms and is destroyed cyclically has been one of the central topics of its study. A planet this close to its star is subject to brutal atmospheric erosion. Ultraviolet radiation and stellar winds constantly sweep the upper atmospheric layers into space. Webb's detection of carbon dioxide and carbon monoxide signals suggests that some form of atmosphere is currently present, probably maintained by continuous volcanic outgassing from the planet's volcanic interior. It is a dynamic atmosphere, in balance between volcanic production from below and stellar erosion from above, an atmosphere that has probably had very different compositions throughout the planet's history and could be entirely different within a few million years. 55 Cancri was also the first rocky planet for which a surface temperature map was built from phase curve observations, measuring how the brightness of the system varies as the planet orbits and presents different viewing angles. The resulting temperature map, published in 2016 from Spitzer data, showed an unusual temperature distribution. The hottest point was shifted eastward from the substellar point, suggesting heat redistribution in the planet, energy transport from the hot side to the cool side through movements in the lava ocean or in the atmosphere. It was the first temperature map of the surface of a rocky planet outside the solar system. A map of a lava ocean, seen from 40 light-years away, built from photons that traveled for 40 years to reach our telescopes. The 55 Cancri system is also remarkable in that the planet is not alone. 55 Cancri has 4 additional planets in orbit, making this system one of the richest in known planets outside the solar system. The outermost planet, 55 Cancri d, has a mass of nearly 4 Jupiter masses and orbits at a distance of 11.5 astronomical units, farther than Saturn's orbit. Between that distant giant and the scorching 55 Cancri e, 3 intermediate planets orbit at various masses and compositions. The complete system is a miniature sample of the planetary diversity that a single protoplanetary disk can produce, from the super-Earth of incandescent lava in the interior to the cold gas giant in the exterior, with several intermediate worlds of still largely unknown nature. The star 55 Cancri is visible, on the darkest nights, to the naked eye from Earth, with an apparent magnitude of just under 6, right at the limit of what the unaided eye can detect under ideal conditions. Under the same star that we can sometimes glimpse with the naked eye in the night sky, this world of lava and possible diamonds turns, completing its 17-hour orbit in perfect and ancient indifference. It is 40 light-years away. If we send a radio signal there today, it would arrive in the year 2065. The reply would arrive in 2105. Any dialogue with that system, if there were ever anything to have a dialogue with, would unfold over timescales that exceed any individual human life. The density of 55 Cancri e, calculated from its mass and radius, is approximately 6.4 grams per cubic centimeter, comparable to Earth's 5.5. This is consistent with a predominantly rocky planet, though the exact composition of those rocks depends critically on the carbon-to-oxygen ratio of the formation disk, which remains uncertain. It is possible that 55 Cancri e is a carbon-rich planet with a silicon carbide interior and perhaps a diamond layer. It is also possible that it has more conventional silicates, similar to Earth in composition but with a lava ocean at the surface instead of water. The distinction between these two possibilities requires more precise spectroscopic measurements of the atmosphere and surface, measurements the James Webb Space Telescope is in the process of providing. What Webb has already shown is that the planet is more variable and more active than simple static models suggest. Brightness variations between transits indicate that the surface or atmosphere changes on timescales of weeks to months, possibly reflecting the irregular advance and retreat of lava flows across the surface, or periodic variations in volcanic outgassing rates. 55 Cancri e is not a fixed, frozen object. It is a living, churning world, even if that life is made of rock and fire rather than carbon and water. There is something singularly evocative about the image of 55 Cancri E, a world that might harbor in its interior one of the most ordered and perfect structures that nature produces, the carbon crystals we call diamonds, wrapped in an ocean of molten chaos, bathed in radiation that gives no respite. Beauty trapped inside chaos. Crystalline order beneath the surface of liquid disorder. It is not a metaphor the universe constructed deliberately, of course. But it is real. And in the quiet of this night, it is worth holding in your mind as the day dissolves. There is a planet 64 light years away that, if you could see it from space, would remind you of Earth. Not because of its size, it is significantly larger, a substantial hot Jupiter. Not because of its temperature, its atmosphere is over 1,000 degrees Celsius. But because of its color. HD 189733b has a deep, vivid blue, similar to the blue of an ocean seen from orbit. It is one of the most beautiful objects in the iconography of exoplanet astronomy. And it is also one of the most lethal. The blue of HD 189733b doesn't come from water. It comes from silicate particles, essentially molten quartz, suspended in its atmosphere, which scatter blue light more efficiently than red. And those particles, driven by the fastest winds ever measured in any known exoplanetary atmosphere, fall as rain. Rain of quartz glass crystals, at 5,400 miles per hour. HD 189733b was discovered in 2005 using the radial velocity method, and has since become one of the most studied exoplanets in the history of science. Partly because its host star, HD 189733, is relatively close and bright by the standards of stars with known planets, facilitating high-precision observations. Partly because the planet is large and orbits very close to its star, producing easily detectable transit and secondary eclipse signals. And partly because, as observations have accumulated, HD 189733b has proven to be extraordinarily rich in surprising atmospheric phenomena. The planet has a mass of approximately 1.13 Jupiter masses and a radius of 1.1 Jupiter radii, slightly more massive and the same size as Jupiter. It orbits its star at a distance of just 31 thousandths of the Earth-Sun distance, completing an orbit in 2 days and 2 hours. Like all hot Jupiters in such close orbits, it is tidally locked, one side always facing the star, the other always in darkness. The dayside temperature is approximately 1,200 degrees Celsius, the night side, around 950. The difference is relatively small compared to other hot Jupiters like WASP 76b, a sign that there is efficient redistribution of heat from the illuminated side to the dark side through the winds. And those winds are extraordinary. Atmospheric circulation models for HD 189733b predict winds of up to 12,000 miles per hour in the upper atmospheric layers, and observations are consistent with those predictions. 12,000 miles per hour is 3.5 miles per second. For comparison, wind on Earth rarely exceeds 250 miles per hour even in the most intense hurricanes. The fastest winds recorded on any planet in the solar system are those of Neptune, at approximately 1,300 miles per hour. The winds of HD 189733b exceed them by a factor of nearly 10. It is the difference between a gentle breeze and an atmospheric tsunami. In those winds travel the particles responsible for the planet's blue color. The determination of HD 189733b's color was published in 2013 by a team at the University of Cambridge's Institute of Astronomy, led by Tom Evans. Using the Hubble Space Telescope, the team measured the planet's reflectance at different wavelengths during the secondary eclipse, the moment when the planet disappears behind its star. By comparing the light of the system with the planet visible and without the planet, they determined what fraction of the starlight was reflected by the planet and at which colors. The result was that the planet reflects blue light more efficiently than red or green, a spectral albedo consistent with the presence of silicate particles in the atmosphere that scatter light the same way oxygen and nitrogen molecules in Earth's atmosphere scatter sunlight and make the sky blue. But the scattering mechanism on HD 189733b is different from Earth's blue sky. On Earth, the blue of the sky results from Rayleigh scattering, the scattering of light by molecules much smaller than the wavelength of visible light. On HD 189733b, the particles producing the blue color are the silicate grains in the atmosphere, submicron-sized particles of molten quartz or other silicon compounds that condense in the cooler upper atmospheric layers. These particles are solid or semi-liquid, are swept along by the supersonic winds, and when the temperature drops low enough, they precipitate, they rain, downward in a process analogous to water precipitation on Earth, but with a violence that has no comparison to any terrestrial weather phenomenon. The glass rain on HD 189733b is not a gentle rain. The particles fall within a wind of 5,400 miles per hour, a speed measured directly through the Doppler effect on spectral lines during transits, in observations published by the team of Tom Loudon and Peter Wheatley at the University of Warwick in 2015. Those observations measured with great precision the broadening and shifting of the sodium and potassium spectral lines at the two edges of the planet's terminator, and found a velocity difference of several kilometers per second between the receding edge and the approaching edge, the direct signature of a wind blowing at thousands of miles per hour in the direction of the global atmospheric flow. It was the first direct measurement of wind speed in an exoplanet atmosphere using the Doppler effect. Under those conditions, the quartz glass particles don't fall gently. They are propelled horizontally by the winds at velocities that turn them into projectiles. In terms of kinetic energy, a microscopic silica particle moving at 2 miles per second has more energy per unit mass than a high-velocity rifle bullet. The rain of HD 189733b is, in practice, a storm of ballistic energy sand, horizontal, endless, driven by a wind that never stops because it has no reason to stop. The temperature imbalance between the two hemispheres of the synchronously rotating planet is permanent and constant. HD 189733b was also one of the first exoplanets in which water was detected in the atmosphere, in Spitzer Space Telescope observations published in 2008. It was also among the first in which methane and carbon dioxide signals were found, and one of the first for which a temperature map of the atmosphere was built from phase curve observations. The temperature map showed that the hottest point in the atmosphere was shifted about 16 degrees east of the substellar point, consistent with models predicting that atmospheric circulation winds shift the temperature maximum toward the trailing side. It was the first observational confirmation of that theoretically predicted shift. What HD 189733b has contributed to exoplanet science is difficult to overstate. It was the test bed on which the techniques of transmission spectroscopy and phase curve analysis were developed and validated that are now applied to dozens of other planets. It was on this planet that humanity first saw the color of an alien world, the deep blue of glass rain and supersonic winds. It was here that the wind speed in another planetary atmosphere was first measured directly. It was here that water molecules in an exoplanet were first confirmed, and where the first temperature map of an exoplanet atmosphere was built with resolution sufficient to detect the shifted hotspot. Each of those results was, in its moment, the first of its kind. The first color. The first directly measured wind. The first confirmed water. The first temperature map with a shifted hotspot. In the catalog of firsts, HD 189733b occupies a singular place. A blue planet, beautiful from a distance, terrifying at any conceivably closer distance. Glass falling in a wind at speeds that have no name in the lexicon of terrestrial meteorology. And yet studied, understood, mapped, its winds measured and its colors determined by instruments built by human beings on a small planet 64 light-years away. HD 189733b has also been the subject of magnetic field studies. In 2020, a team detected variations in the depth of the planet's transit at X-ray wavelengths inconsistent with the expected planet size. The most plausible interpretation was that the planet's magnetic field was interacting with the stellar wind in a way that created an extended magnetosphere, a bubble of magnetic field enveloping the planet that was detectable in X-rays. If confirmed, it would be the first detection of an exoplanet's magnetosphere. The existence of that magnetosphere would have implications for the planet's atmospheric evaporation rate. A strong magnetic field protects the atmosphere from stellar wind erosion, much as Earth's magnetic field shields us from the solar wind. One of the most unsettling aspects of HD 189733b, if one allows oneself to imagine the visceral experience of being there, is the absolute uniformity and inescapability of the weather. The wind always blows in the same direction. The crystals always fall in the same hemisphere. The Terminator is always in the same place. There are no seasons, because there is no meaningful axial tilt. There is no diurnal variation because the planet doesn't rotate relative to its star. The weather on HD 189733b is the same today as it was a billion years ago and as it will be a billion years from now. An eternal, unchanging meteorology, the only clock being the slow cooling of the planet's interior over cosmic time. Rest with that image. The perfect blue of a planet that is not yours. The winds that never stop. The glass that falls. And the distance that makes it all silent, beautiful, completely harmless from here. There are planets that impress by their violence, by their rains of metal, by their winds that exceed any terrestrial reference, by their surfaces of incandescent lava. And there are planets that impress by something subtler and stranger, by their behavior in the face of light. Kepler 7b belongs to this second category. It is not the hottest, or the coldest, or the largest. But it has a property that makes it unique among the thousands of known exoplanets. It is the most reflective planet we have ever found. It reflects its star's light with an efficiency that surpasses even Venus, the brightest planet in our solar system, whose sulfuric acid clouds act as a nearly perfect mirror. And the reason for that extraordinary reflectivity is one of the most elegant and unexpected observational results in the history of exoplanet characterization. Kepler 7b was discovered by the Kepler telescope in 2010, being one of the first exoplanets confirmed by that mission. It orbits a star slightly more massive and hotter than the Sun, Kepler 7, located approximately 1,000 light-years away in the constellation Lyra, at a distance of about 6% of the Earth-Sun distance, completing an orbit in 4.5 days. It is a low-mass hot Jupiter. It has approximately 434 Earth masses, roughly 1.4 Jupiter masses, but its radius is 1.7 Jupiter radii. That makes it one of the lowest density known planets, with a density of just 0.6 grams per cubic centimeter, less than water, less than half the density of Jupiter. It is, in colloquial terms, a puffy planet. The low density of Kepler 7b is a consequence of its heavily inflated atmosphere, swollen enormously under the influence of the heat from its nearby star. The equilibrium temperature of the planet, the temperature it would have if it were a perfect absorber of stellar radiation, is approximately 1,600 Kelvin. But the actual temperature of its upper atmosphere, measured from secondary eclipse observations with Spitzer, is lower than that equilibrium temperature, indicating that the planet reflects a significant fraction of the stellar energy it receives rather than absorbing it. It is brighter than it should be. Something in its atmosphere is reflecting its star's light with extraordinary efficiency. The answer came in 2013, with the publication of results from Kepler 7b observations using the Spitzer telescope in 2 infrared bands. The team led by Bryce-Olivier Demery of the Massachusetts Institute of Technology built from those observations the first east-west resolved temperature map of an exoplanet, the first map that could distinguish between the eastern and western halves of the visible hemisphere of the planet. And what they found was unexpected. The brightest point on the planet was not at the center of the illuminated hemisphere, where temperature is highest, but clearly shifted to the west. The western side of the planet was significantly brighter than the eastern side. This asymmetry had an immediate and elegant interpretation: clouds. Not clouds distributed uniformly throughout the atmosphere, but clouds concentrated in the western hemisphere of the planet. Highly reflective clouds, with reflectivity properties similar to high-altitude water clouds on Earth, or perhaps like the silicate clouds that form in high-temperature atmospheres, located specifically in the western half of the planet's day side. It was the first direct detection of clouds on an exoplanet. Not an indirect inference from the shape of the spectrum, but a direct detection from the spatial distribution of the planet's brightness. The western side was brighter because the clouds were there and reflecting starlight toward us. Why are the clouds on the western side and not distributed uniformly? The answer lies in the planet's atmospheric dynamics. Circulation models for hot Jupiters predict that, in planets with strong stellar irradiation and synchronous rotation, the winds create a characteristic circulation with a high-speed jet flowing from the day side to the night side over the poles, and return currents at mid-latitudes. In this circulation, the hottest point in the atmosphere tends to be shifted eastward of the substellar point, because winds carry the heat in that direction. But clouds form where the temperature is low enough for compounds to condense, and that happens on the western side, where the relatively cool material from the night side hemisphere is dragged toward the illuminated hemisphere by the return currents of the circulation. The western side is the region where cool air from the dark side enters the illuminated side. and it is there that condensation and cloud formation are most favored. Kepler 7b has a geometric albedo, the fraction of incident light it reflects directly back toward the source, of approximately 0.35. For comparison, the Moon has a geometric albedo of 0.12, and Venus of 0.65. Kepler 7b sits between the two most reflective planets of the solar system. But its reflectivity doesn't come from Venus's sulfuric acid clouds or from the bright regolith of some solar system moons. It comes from high-temperature silicate clouds, possibly crystals of enstatite or quartz, floating in the upper layers of its hot atmosphere and reflecting starlight with remarkable efficiency. The scientific story of Kepler 7b illustrates something broader about the exoplanet era, the ability to extract extraordinary amounts of information from extraordinarily small signals. The planet is 1,000 light-years away. Its angular diameter as seen from Earth is inconceivably small, equivalent to the diameter of a dime seen from 60,000 miles away. It is, for all current instruments, completely unresolvable as a disk. And yet we know its size, its mass, its density, its average temperature, the spatial distribution of its clouds, the location of its brightest point, and can infer from all of this the dynamics of its atmospheric circulation. All of that from fluctuations in the brightness of its star, fluctuations representing changes of less than 1% in the light reaching our telescopes. Astronomers who work with exoplanets are, in a certain sense, craftspeople of information. They take tiny signals, brightness variations, wavelength shifts of fractions of an angstrom, temperature changes of tenths of a degree in cryogenic detectors, and build from them maps, profiles, stories. The story of Kepler 7b is one such construction, a cloud map of a world we will never see directly, woven patiently from photons that traveled 1,000 years to reach our detectors. Kepler 7b is 1,000 light-years away. The light it reflects right now will reach Earth in 1,000 years. The people who receive it haven't been born yet. And yet the planet is already shining, already reflecting, already carrying its clouds on the western side where the atmospheric circulation concentrates them, as it has for billions of years and as it will for billions more. The James Webb Space Telescope has Kepler 7b in its observing program, and Webb's observations are expected to dramatically improve the spectral resolution and quality of the planet's temperature map. Webb can observe across a broader range of infrared wavelengths than Spitzer, allowing it to distinguish between different types of clouds, pure silicate clouds, iron oxide clouds, magnesium compound clouds, based on differences in how each cloud type absorbs and emits radiation in the infrared. The cloud map of Kepler 7b that Webb is building will be the most detailed ever produced of an exoplanet atmosphere. There is something in that which resembles sleep. The effortless continuity. The brightness without intention. The reflection as nature, not as action. Kepler 7b shines because that is what it does. It exists in its 4.5-day orbit, with its western clouds and its vivid blue-white light, needing nothing more. Astronomers who work with exoplanets are, in a certain sense, craftspeople of information. They take tiny signals, brightness variations, wavelength shifts of fractions of an angstrom, temperature changes of tenths of a degree in cryogenic detectors, and build from them maps, profiles, stories. The story of Kepler 7b is one such construction, a cloud map of a world we will never see directly, woven patiently from photons that traveled 1,000 years to reach our detectors. Every pixel of that map represents thousands of measurements, hours of telescope time, months of data analysis, and at the end of it all, clouds. Western clouds on a planet 1,000 light-years away. Clouds that are real, that have been there for billions of years, that don't know and don't care that we found them. There is also a kind of comfort in the scale. Kepler 7b's clouds are not going anywhere. They will be there next year, and next century, and 1,000,000 years from now, shifted slightly west by the same atmospheric circulation that has been running without interruption since before Earth's continents were in their current configuration. In a universe full of things that change and end, the western clouds of Kepler 7b are, for all practical purposes, permanent. A fixture of the cosmos as reliable as the orbit of the moon or the fusion at the core of the sun. Kepler 7b is 1,000 light-years away. The light it reflects right now will reach Earth in 1,000 years. The people who receive it haven't been born yet. And yet the planet is already shining, already reflecting, already carrying its clouds on the western side where the atmospheric circulation concentrates them. Close your eyes now. Imagine that blue-white glow, 1,000 light-years away. Soft, constant, eternal on any scale that matters tonight. In the catalog of strange worlds, there is a category that challenges even the definition of what we believe a planet to be. Every planet we have visited so far on this journey has one thing in common: it orbits a star. Each has a sun, however near or far, however cool or scorching. Each has a source of light, a reference point, a center around which it turns. But there are planets that have none of this. Planets that travel alone through interstellar space, with no star, no external light, no heat other than the residual warmth of their own formation. Planets that are, in the most absolute sense, worlds of darkness. They are called rogue planets, or free-floating planets, and they are possibly the loneliest objects in the known universe. The idea that planets without stars might exist emerged from theoretical models of planetary formation before there were any observations to support it. The models described how, in the first millions of years of a planetary system's life, the protoplanetary disk can contain dozens of embryonic bodies of planetary mass that interact gravitationally with one another. These gravitational interactions are, in essence, a cosmic version of a multi-body billiard game. Every close encounter transfers angular momentum between the participants. In some cases, the dynamics result in two planets merging. In others, they produce well-separated stable orbits. And in others, a planet receives enough gravitational impulse during a close encounter to reach the escape velocity of the system and be ejected into interstellar space. The ejection of planets during solar system formation was, in fact, probably very common in our own system. Models of the primitive solar system, especially the NICE model on the Grand TAC, predict that the solar system originally had more planets than it does today, and that several were ejected during the orbital reshuffling that occurred roughly 700 to 800 million years after the Sun's formation. So the solar system may have contributed one or several worlds to the galaxy's population of rogue planets billions of years ago, worlds now traveling through interstellar space that we cannot track. The first observational detections of rogue planet candidates came in the early 2000s, through gravitational microlensing surveys toward the galactic center. Microlensing is a phenomenon predicted by general relativity, when a massive object passes between us and a more distant background star. The object's gravity acts as a lens and temporarily amplifies the brightness of the background star. The duration and shape of the brightness flash depends on the mass of the lensing object. Jupiter-mass planets produce flashes lasting a few days. Earth-mass planets produce flashes lasting hours. And if the lensing object is not associated with any star, if it is a rogue planet, the flash lacks the additional signature of a host star. In 2011, the MOA and OGLE teams, monitoring millions of stars in the galactic bulge for microlensing events, published the analysis of a sample of short-duration events with no detectable host star. They found a statistical excess of such events consistent with the presence of a population of Jupiter-mass objects, Jupiter-sized planets, traveling freely through the galaxy with no stellar host. The estimate was provocative. If their statistics were correct, there were at least as many free-floating Jupiter-mass planets in the galaxy as there were stars. Possibly more. A galaxy full of dark worlds, invisible except for the fleeting effect of their gravity on the brightness of distant stars. Subsequent observations with more sensitive microlensing programs have refined that estimate. The Euclid Space Telescope, launched by the European Space Agency in 2023, includes among its scientific objectives the detection of rogue planets through microlensing, with a sensitivity that could detect Earth-mass planets, Earth-sized planets traveling alone through interstellar space. If current estimates are correct, the number of Earth-mass rogue planets in the galaxy could exceed the number of stars by several orders of magnitude. The Milky Way could have 100 billion or more Earth-mass rogue planets. For a rogue planet ejected from its system billions of years ago, that never had much of an atmosphere to begin with, the answer is probably bleak, a rocky or icy body at temperatures of tens of degrees above absolute zero, with no atmosphere, nothing to distinguish it from a very large asteroid except its mass. A dead world, frozen to its depths, traveling in absolute silence. But for a more massive rogue planet, one with the mass of Jupiter or greater, the story is more interesting. Massive planets retain internal heat for billions of years after their formation. Jupiter, for example, radiates into space more energy than it receives from the Sun, because it is still cooling from formation. A Jupiter-mass rogue, with no star, would still be a source of internal heat for billions of years. Its upper atmosphere would be cold, perhaps 150 to 200 Kelvin, but its deeper layers would be warm, and convection inside the atmosphere could generate complex weather, clouds, winds, storms, driven by internal heat rather than stellar heat. In 2023, the James Webb Space Telescope revolutionized the study of rogue planets with direct imaging of several dozen planetary mass objects in the Orion star-forming region. Using Webb's NIRCam instrument to observe in the near-infrared, wavelengths at which warm objects like rogue planets emit detectable thermal radiation, the team found over 100 objects with masses between 5 and 10 times Jupiter's that appeared to be unbound to any star. Many of them appeared in pairs, orbiting each other at large separations, a configuration that raises questions about whether they formed as planets ejected from protoplanetary systems or as substellar objects formed directly from the collapse of a gas cloud, the same way stars form but at masses too small to ignite nuclear fusion. The distinction between a massive rogue planet formed by ejection and a low-mass brown dwarf formed by direct gas collapse is, in some cases, blurred to the point of near observational irrelevance. But conceptually it matters. An ejected planet was once part of a system, perhaps had companions, perhaps passed near smaller planets before being flung into the void. A low-mass brown dwarf never had that context. It was always a solitary, an object halfway between star and planet that the universe formed and abandoned without further history. One of the most unsettling aspects of rogue planets is their practical invisibility. An Earth-mass rogue planet traveling through interstellar space emits virtually no detectable radiation. It has no star to illuminate it and produce transits. It has no star whose radial velocity it perturbs. It has insufficient internal heat to glow in the infrared at detectable levels from interstellar distances. It can only be detected through microlensing, the brief flash of a chance alignment with a background star, or, if it approached close enough to the solar system, through direct observations of very cold bodies in the far infrared. A rogue planet could have passed within a light year of the solar system in the last million years without our detecting it, and more could be approaching, equally invisible until some future instrument can track them. The Vera C. Rubin Observatory, which began full operations in 2024 and 25, monitors the southern sky with unprecedented cadence and depth. Rubin will detect microlensing events of hours today's duration at a frequency that previous programs could not achieve, providing the largest sample of Earth-mass rogue planet candidates ever assembled. Early Rubin results promise to redefine estimates of rogue planet abundance in the galaxy. There is something profoundly moving, if one allows it, in the image of the rogue planet. A world that has traveled in darkness for billions of years, with no light to illuminate it from outside, no heat to warm its surface from above. Only the cold of interstellar space, the photons of the cosmic microwave background as its sole radiation bath, and the residual heat of its interior cooling slowly across the eons. If it had moons, and some might, captured or co-formed, those moons would be in a darkness so complete that the concepts of day and night would carry no meaning. There would be only the faint glow of the planet itself in the infrared, and beyond that, the absolute darkness of interstellar space, scattered with stars too distant to warm anything. The discovery of Oumuamua in 2017, and of the interstellar comet Borisov in 2019, showed that interstellar space sends visitors to the solar system more frequently than previously thought. Those two objects were relatively small, asteroid or comet-sized, and arrived from interstellar space, crossed the inner solar system, and left. If small objects can make that journey, rogue planets can too, only at much greater distances and without entering the inner orbits. Models predict that the solar system has had close encounters with planetary mass objects at distances of a fraction of a light year throughout its history, and that those encounters, while rarely close enough to significantly alter the orbits of the planets, could have left subtle traces in the distribution of objects in the Oort cloud. The search for rogue planets is being transformed by the Vera C. Rubin Observatory, which began full operations in 2024 and 5. Rubin monitors the southern sky with unprecedented cadence and depth, detecting microlensing events of hours today's duration at a frequency that previous programs could not achieve. It is expected to produce the largest sample of Earth-mass rogue planet candidates ever assembled, and to allow the first statistically meaningful measurements of the mass function of free-floating planetary objects in the galaxy, the distribution of how many rogue planets there are at each mass. The answers, when they come, will either confirm that the galaxy is teeming with billions of dark, wandering worlds, or surprise us with a very different picture. Billions of them, perhaps, traveling in the dark across the Milky Way, passing through the solar neighborhood every few million years. Most too far to detect with current instruments. Some identified by the fleeting shadow of their gravity on a distant star. Anonymous, cold, perpetually alone. The universe makes more worlds than it can give light to. 71% of Earth's surface is covered by water. Earth's oceans have an average depth of about 2.5 miles. Beneath that ocean there is rock, ocean floors, continental shelves, the upper mantle. Earth's water is, in terms of total mass, a tiny fraction of the planet, less than 0.02% of Earth's total mass. We are, in terms of overall composition, a fundamentally rocky planet with a thin film of water on the surface. But there are planets in the galaxy where water is not a thin film, where the water doesn't end at a few miles depth, where the water goes down miles and miles and miles, hundreds of miles, until the pressure converts it into forms of ice that don't exist anywhere on Earth. And beneath that there is more water in a supercritical fluid state, and beneath that perhaps a small rocky core or perhaps nothing solid at all. These planets are called ocean worlds, and models predict they could be one of the most common types of planets in the galaxy. The ocean world category is not defined by a specific percentage of water coverage, but by the fraction of the planet's total mass that is water. For Earth, that fraction is approximately 0.02%. An ocean world, in the definition planetologists use, has a water mass fraction of at least 1% of the total mass, and in the most extreme cases, 10 to 50%. For an Earth-sized planet, 10% of its mass in water amounts to a global ocean hundreds of miles deep. That is enough for the ocean floor, under the pressure of hundreds of miles of water above it, to be at pressures of several gigapascals, pressures at which water cannot exist as liquid or vapor, but in forms of high-pressure ice called Ice 6, Ice 7, Ice X, ices that are denser than liquid water and that form layers in the planet's interior. The first serious ocean world candidate detected was GJ1214b, discovered in 2009 by the M-Earth Project, a search program for planets around red dwarf stars. GJ1214b has a mass of approximately 6 Earth masses and a radius of 2.7 Earth radii. It orbits a faint red dwarf about 42 light-years from Earth. The combination of its mass and radius gives a density of approximately 2 grams per cubic centimeter, significantly lower than Earth's density of 5.5. A density of 2 grams per cubic centimeter is inconsistent with a purely rocky planet, which would have a higher density. The most natural interpretation is that the planet contains a significant fraction of materials less dense than rock, water, ice, light compounds, or some combination. Interior structure models consistent with the observed density include versions where the planet has a small rocky core surrounded by a high-pressure ice layer several hundred miles thick, covered by a deep liquid ocean, covered in turn by a water vapor-rich atmosphere. Confirmation of GJ1214b's nature was difficult for spectroscopic reasons. In initial transit observations with Hubble, the transmission spectrum of the planet's atmosphere showed a striking absence of molecular features. The spectrum was flat, without the water vapor or methane absorptions expected from an atmosphere of known composition. The most accepted interpretation was that GJ-1214b's atmosphere was blanketed by a layer of clouds or haze that blocked the view of the lower layers where the absorbing molecules would be found. An opaque atmosphere is a frustrating barrier for transmission spectroscopy, because the technique depends precisely on being able to see through the outer layers. The clouds hiding GJ-1214b's atmospheric composition had made it one of the most difficult atmospheres to characterize in the exoplanet catalog. The James Webb Space Telescope partially resolved the mystery of GJ-1214b in 2022. Using the MIRI instrument to observe the planet in the mid-infrared, wavelengths at which water and other compounds have their most characteristic spectral signatures, the team led by Eliza Kempton built the first detailed phase curve of this planet. What they found was that the temperature contrast between the dayside and nightside hemispheres was much smaller than would be expected for a planet with no atmosphere or a very thin one. There was efficient heat redistribution between the two hemispheres, requiring an atmosphere with enough mass to transport energy effectively. Moreover, the phase curve in the infrared had a shape compatible with an atmosphere rich in heavy molecules, water vapor, methane, carbon dioxide, rather than one dominated by hydrogen and helium. It was the first direct evidence that GJ-1214b has a heavy molecular atmosphere, consistent with a water world outgassing its aqueous interior. Beyond GJ-1214b, there are other intriguing candidates in the catalog. Kepler-62f, one of the planets in the Kepler-62 system about 1,200 light-years away, is a super-Earth-sized planet in the habitable zone of its star, the region where temperatures allow liquid water to exist on the surface, with a radius of 1.4 Earth radii and an estimated mass of several Earth masses. Its parameters are consistent with an ocean world in the habitable zone, though the distance of the system makes observational confirmation very difficult. TOI 1452b, discovered in 2022 by a Canadian team and announced as a particularly robust ocean world candidate, has a radius of 1.67 Earth radii and a density of approximately 5 grams per cubic centimeter, lower than expected for pure rock but consistent with roughly 30% of its mass being water. It orbits a star in the constellation Draco just 100 light-years away, making it an accessible target for spectroscopy with Webb. The question of whether ocean worlds are habitable is one of the most actively debated in astrobiology. On Earth, life is unevenly but pervasively distributed through the oceans, from the surface to the hydrothermal vent floors thousands of feet deep. But life on Earth depends ultimately on the carbon silicate cycle. Carbon dioxide from the atmosphere dissolves in the ocean, precipitates as carbonates, is subducted by tectonic plates, and returns to the atmosphere through volcanism, a cycle that regulates climate over millions of years. In an ocean world where the ocean floor is high-pressure ice rather than rock, there is no subduction, no oceanic volcanism, no exchange between the ocean and a rocky interior. The carbon silicate cycle is broken. Could life sustain itself in that environment? We don't know. But the question is serious enough that the detection and characterization of ocean worlds is a priority on the scientific agenda of the coming decades. The study of solar system moons has provided the best available analogs for exoplanetary ocean worlds. Europa, a moon of Jupiter, has a liquid water ocean under an ice crust about 60 miles thick, kept liquid by the tidal heat generated by Jupiter's gravity. Enceladus, a moon of Saturn, has a subsurface ocean that expels material into space through geysers at its south pole, material that includes water vapor, carbon dioxide, methane, and even silicon grains indicating hydrothermal activity at the ocean floor. Titan has lakes and seas of methane and ethane on its surface. Callisto, Ganymede, and possibly Pluto have layers of saltwater ocean in their interiors. The solar system is, in a sense, a miniature catalog of ocean worlds, and studies of those moons directly inform the models of exoplanetary ocean worlds. Astrobiology dedicated to thinking about what kind of biochemistry could function in deep water, high-pressure, lightless environments has produced some intriguing frameworks. On Earth, hydrothermal vent ecosystems thrive without sunlight, driven by chemical energy from the Earth's interior, primarily the oxidation of sulfur and hydrogen compounds. In an ocean world, if the rocky core is geologically active enough, there could be hydrothermal vents at the ocean floor, or more precisely, at the interface between the liquid ocean and the high-pressure ice layer, providing enough chemical energy to support primitive ecosystems. It is a speculative possibility, but it is anchored in the reality of the hydrothermal vent ecosystems we know on Earth. Imagine the surface of an ocean world in the habitable zone of its star. There is no land, no beach. The horizon is water in every direction, as far as the eye can reach and beyond, at every latitude, every meridian. The sky may be different colors depending on the atmospheric composition, perhaps orange if methane is abundant, perhaps reddish if the star is a red dwarf, perhaps slightly different from the terrestrial blue if the air composition varies. And beneath the surface, miles and miles of water, darkening progressively as sunlight no longer reaches the deepest layers. And further down, the absolute silence of high-pressure ice, and beneath that perhaps a small, dark core, a reminder that this world has an interior as well as its infinitely liquid surface. An ocean with no visible bottom, on a planet with no continents, under a sky that is not exactly Earth's. One of the most potentially habitable worlds imaginable, and at the same time one of the most radically alien to any experience that the history of life on Earth has ever known. Life there, if it existed, would have to be entirely aquatic. Never any dry land. No evolution of terrestrial locomotion. No hands, no tools, no fire. Just the ocean, forever. There is also a more exotic class of ocean world worth holding in mind, not planets with water oceans, but planets with oceans of other liquids entirely. Titan, Saturn's largest moon, has lakes and seas of liquid methane and ethane on its surface, a world with rainfall, rivers, coastlines, and weather cycles, all using methane as the working fluid instead of water. In colder exoplanetary environments, at the right temperatures and pressures, other compounds can exist as liquids, ammonia, nitrogen, even hydrogen. The variety of fluids that can constitute a planetary ocean is, in principle, as rich as the catalog of compounds that can exist in liquid form under the pressure and temperature conditions characteristic of planetary surfaces, which in turn depend on the planet's mass and its distance from its star. For all their strangeness, ocean worlds represent something important in the search for life. Water is the solvent of terrestrial biochemistry. It is the medium in which biochemical reactions occur. It is the primary component of every living cell on Earth. A planet entirely covered by a deep global ocean, with the right temperature and chemistry, is, for an astronomer searching for life, the most attractive destination that can be imagined. The fact that such planets exist, and that serious candidates are within the observational reach of current telescopes, is one of the most exciting realities of the exoplanet catalog. Breathe. The water rises and falls. Ocean worlds turn in their orbits, covered in liquid silence. Somewhere in the galaxy, at a distance that light takes years to cross, a deep ocean reflects the faint glow of a red dwarf and keeps its secrets beneath miles of dark, still water. There is a range of planetary sizes that our solar system, for reasons astronomers still debate, did not produce. Between the radius of Earth, one Earth radius, and the radius of Neptune, approximately 4 Earth radii, our solar system has a surprising gap. Mars, the smallest of the outer planets, has barely half the radius of Earth. Neptune has 4 times Earth's radius. Between those two sizes there is nothing in our solar system. But in the universe there is everything. Exoplanets fill that space with bewildering abundance. They are the most common planets detected by Kepler, the most prevalent in test catalogs. The universe loves the sizes our solar system ignored. Those planets carry 2 names, depending on which direction you approach their nature from. Seen from below, from Earth's size upward, they are called super-Earths, rocky planets more massive and larger than Earth, with masses up to roughly 10 Earth masses and radii up to about 1.5 to 2 Earth radii. Seen from above, from Neptune downward, they are called mini-Neptunes or sub-Neptunes, planets with significant gaseous or water envelopes, smaller than Neptune, with radii between 1.5 and 4 Earth radii. The distinction between a massive super-Earth and a small mini-Neptune depends on whether the planet does or does not have a significant gaseous or aqueous envelope, and that is precisely what turns out to be difficult to determine from remote observations. The distribution of planet sizes detected by Kepler revealed something extraordinary and completely unexpected: a statistical gap in the distribution of planetary radii around 1.5 to 2 Earth radii. This gap, called the Fulton Gap, after Benjamin Fulton, who identified it clearly in 2017, divides the planet population into 2 distinct groups. Planets smaller than about 1.5 Earth radii tend to be dense and rocky, consistent with iron and silicate compositions with no appreciable gas envelope. Planets larger than about 2 Earth radii tend to have lower densities, consistent with the presence of a water or gas envelope that inflates their size beyond what rock and metal alone would allow. The most widely accepted interpretation of the Fulton Gap is that it reflects the process of atmospheric photoevaporation. Planets in the 1 to 2 Earth radii range that orbit close to their star are exposed to the ultraviolet and X-ray radiation emitted by the star, especially during its first hundreds of millions of years when it is most active. That radiation can heat and evaporate the gaseous envelope of a sufficiently small planet. Planets that have enough rocky mass to hold onto their envelope under that irradiation become robust mini-Neptunes. Planets that don't have sufficient mass lose their envelope and are left as bare rocky super-Earths. The Fulton Gap is, in this model, the boundary between planets that survived photoevaporation and those that were stripped by it. It is a division not of original composition but of history, what survived the early stellar blast and what did not. Some of the most fascinating worlds in the exoplanet catalog fall in this size range. LHS 1140b, 49 light-years away in the constellation Cetus, is a super-Earth of 1.73 Earth radii that orbits in the habitable zone of a red dwarf. With a mass of approximately 5.6 Earth masses and a density consistent with a predominantly rocky composition, it is one of the best-known candidates for a rocky habitable planet outside the solar system. Webb has begun observing its atmosphere, and first results published in 2024 tentatively suggest the possibility of a nitrogen-rich atmosphere, similar to Earth's, though confirmation requires additional observations. The TRAPPIST-1 system is perhaps the most famous in the search for habitable planets. Around an ultra-cool red dwarf, a star so small and faint that its 7 planets, all of Earth to super-Earth size, orbit within distances equivalent to Mercury's distance from the Sun. 3 planets lie in the habitable zone. TRAPPIST-1e, TRAPPIST-1f and TRAPPIST-1g have equilibrium temperatures compatible with the existence of liquid water on the surface under certain atmospheric conditions. The star TRAPPIST-1 is just 40 light-years away, making its planets accessible to transmission spectroscopy with Webb. Results so far have been mixed. Some of the inner planets appear to lack dense atmospheres, perhaps eroded by the red dwarf's activity in its youth. But the habitable zone planets retain the possibility, not yet ruled out, of having some form of atmosphere. The TRAPPIST-1 system occupies hours of Webb observation time each year, and its results are the most anticipated in the field of habitable planet research. The question of what distinguishes a habitable super-Earth from an uninhabitable one has no simple answer. The habitable zone, the band of distances from the star where water can be liquid, is a necessary but not sufficient condition. The planet's composition matters. A pure iron world of 2 Earth masses would not be habitable in the same way as a silicate world with a moderate water content. The history of stellar irradiation matters. A young red dwarf can be so active that it erodes the atmosphere of any planet in its habitable zone before the stellar activity calms. The presence or absence of plate tectonics matters. Tectonics regulate the carbon cycle and keep the climate stable over millions of years. The magnetic field matters. Without one, the stellar wind erodes the atmosphere. The moon matters. Earth's moon is thought to stabilize Earth's axial tilt, preventing catastrophic climate swings that might hinder the development of complex life. Of all those conditions, the only one we can directly observe with current telescopes is the presence and composition of the atmosphere. And even that is hard. Planets in the habitable zones of Sun-like stars are too small and too far from their stars for transmission spectroscopy to be feasible with current instruments. Planets in the habitable zones of red dwarfs, like those of TRAPPIST-1, are more technically accessible, but red dwarfs have their own habitability challenges. They are very active in youth and emit large amounts of ultraviolet radiation and X-rays that can erode atmospheres and damage organic molecules at the surface. The habitability question for super-Earths also has a dimension rarely discussed in mainstream science communication: habitability for complex life, not just for any life at all. The conditions for simple microbial life to exist are probably far more permissive than the conditions for complex life, animals, plants, beings with central nervous systems, to develop and persist. On Earth, microbial life appeared relatively quickly after the crust formed, about 4 billion years ago. Complex life took another 3 billion years. For complex life to emerge, high enough oxygen levels were needed, stable temperature over hundreds of millions of years, the absence of mass sterilizations, and probably many other factors we don't fully understand. A super-Earth could harbor microbial life in its subsurface ocean without having the conditions for complex life at its surface. And only complex life, if it exists, would be detectable from a distance through biosignatures. The most ambitious scientific program planned for the coming decades is NASA's Habitable Worlds Observatory concept, a space telescope of 6 to 8 meters in diameter, capable of directly imaging Earth-sized planets in the habitable zones of nearby Sun-like stars and performing spectroscopy of their atmospheres in search of oxygen, ozone, methane, and water vapor in combinations that would suggest chemical disequilibrium maintained by biological processes. If funded and built on the expected schedule, it could be operational by mid-century, and could provide the first direct observational answer to the question of whether there is life on other super-Earths. Not in some indefinitely distant science fiction future. Possibly within the lifetime of people alive today. The gap between super-Earth and mini-Neptune is, in a sense, the most important frontier in the exoplanet catalog for the search for life. Above it are the worlds of gas and water, possibly habitable in subsurface oceans, but not in the familiar sense of a planet with a surface and breathable atmosphere. Below it are the rocky worlds, candidates for solid surfaces, surface oceans, atmospheres, perhaps life visible from space through biosignatures. The Fulton Gap is, in that sense, not just a statistical feature of the size distribution of planets. It is the dividing line between the worlds of the type we know and the worlds of types we don't. More than 5,000 confirmed exoplanets. Dozens of habitability candidates. Multi-planet systems in the habitable zone. Worlds with names and coordinates and orbital periods and measured densities. Each of them a destination that humanity identified from light years away with instruments that would have seemed like magic a century ago. The night is deep. The galaxy is large. Rogue planets travel in the darkness. Ocean worlds keep their secrets beneath miles of liquid silence. Super-Earths wait, in their habitable zones, for someone with better instruments than ours to discover what is in them. Sleep. The cosmos does not need your vigil tonight. There is an experience shared by every living thing that has ever existed on Earth, from the first organisms 4 billion years ago to every human being who has lived, the cycle of day and night. Earth's rotation on its own axis makes the sun rise every morning and set every evening, marking the rhythm of life with a regularity so constant it has become the foundation of all terrestrial biology. Circadian rhythms, the internal biological cycles of approximately 24 hours that regulate sleep, metabolism, body temperature, hormonal secretion, exist precisely because life evolved on a planet where light and darkness alternated with predictable periodicity. Day and night are so fundamental to life on Earth that it is almost impossible to imagine existence without them. And yet the majority of potentially habitable planets identified so far do not have day and night in that sense. Planets in the habitable zone of red dwarf stars, the smallest, coolest, and most common stars in the galaxy, representing roughly 70% of all stars, orbit so close to their stars that tidal gravity has synchronized their rotation with their orbit. Like the Moon with Earth, they always show the same face to their star. One hemisphere lives in eternal day. The other lives in a night that never ends. The horizon never changes. The sun never moves in the sky. If there is an atmosphere, Weather is driven not by the day-night cycle but by the temperature difference between the two static hemispheres. This phenomenon is called tidal locking, or synchronous rotation, and it is exactly the same process that keeps the moon always showing the same face to Earth. The physical cause is straightforward. If a body is not perfectly spherical, if it has equatorial bulges, irregularities in its mass distribution, oceans that slosh, the more massive gravitating body exerts differential forces on those irregularities that tend to align them with the direction of gravitational pull. Over millions of years, this tidal torque gradually slows the body's rotation until its rotation period equals its orbital period. At that point, the net rotation relative to the gravitating body is zero, and locking is complete. For planets in the habitable zone of red dwarfs, where orbital distances are small and tidal forces proportionally stronger, this process can complete in tens to hundreds of millions of years, fast in geological terms. The habitability of tidally locked worlds has been intensely debated since it was discovered that the habitable zone planets of red dwarfs, like those of the TRAPPIST-1 system, are probably in this state. Scientists' first intuitions were skeptical. If one hemisphere is permanently illuminated and the other permanently dark, wouldn't the entire atmosphere freeze on the night side, condensing as snow in the darkness and leaving the planet atmosphere free? This catastrophe is called an atmospheric collapse, and for years it was one of the main arguments against the habitability of red dwarf worlds. More sophisticated atmospheric models, developed over the past decade, have considerably nuanced that pessimistic picture. Atmospheric collapse only occurs if the atmosphere is too thin to transport enough heat from the day side to the night side. If the atmosphere is sufficiently dense, if surface pressure is comparable to or greater than Earth's, then atmospheric circulation can transport heat from the lit side to the dark side with enough efficiency to prevent the atmosphere from freezing on the night side. Models show that, for surface pressures similar to Earth's, even a tidally locked planet can maintain moderate temperatures in an equatorial band surrounding the terminator, and above freezing temperatures across a significant fraction of the night side. Life, if it existed on such worlds, might concentrate in the terminator region, the perpetual twilight band separating eternal day from eternal night. The terminator region of a tidally locked world is, in certain respects, the most intriguing environment the climate models produce. In that band of permanent twilight, the star is always near the horizon, the sun never sets, but it never rises very high either. The temperature at the terminator is moderated by airflow between the two hemispheres and could be, for a planet with an appropriate atmosphere, within the habitable range for life. Winds blow continuously toward the terminator, from the hot day side to the cool night side, and at the terminator itself the two airflows meet and generate weather systems that could be permanent, similar to Earth's climatic fronts but fixed in space rather than moving around the globe. If there were sighted beings at the terminator of a tidally locked world, if there were anything with eyes on that planet, they would see a sky profoundly different from ours. The star would always be at or just above the horizon, painting the sky in perpetual shades of sunrise and sunset, reds, oranges, golds, never the blue of midday. The background stars, visible on Earth only at night, would be visible in part of the sky even with the sun on the horizon, because the terminator sky is never completely dark nor completely bright. On the night side of the world, stars would always shine, no summer nights, no sunsets, just the permanent stars over a sky that never brightens. The planet TRAPPIST-1e is currently the most serious candidate for a tidally locked, potentially habitable world. It has a radius of 0.92 Earth radii, a mass of approximately 72% of Earth's mass, and orbits in the habitable zone of its star with a period of 6 Earth days. Atmospheric models for TRAPPIST-1e under the assumption of tidal locking in a dense atmosphere show that the planet could have average temperatures at the terminator of between 0 and 20 degrees Celsius, perfectly compatible with liquid water and most biological processes we know. Webb has begun observing the atmosphere of TRAPPIST-1e, and initial results, though still tentative, do not rule out the presence of a dense atmosphere. The red dwarf TRAPPIST-1 also reminds us that tidal locking is not the only habitability challenge these stars present. Red dwarfs are prone to stellar flares, violent outbursts of ultraviolet radiation, and energetic particles that can be much more intense, in relative terms, than those of the Sun. For a planet in the habitable zone of a red dwarf, orbiting at just 4 or 5% of the Earth-Sun distance, an intense stellar flare can bombard the surface with doses of ultraviolet radiation that would be lethal to unprotected life. If the planet has a strong magnetic field, most particles would be deflected. If not, the surface would be directly exposed. The question of whether the magnetic fields of tidally locked planets are strong enough to provide protection against their stars' flares is one of the most actively investigated in exoplanet astrophysics. Planetary magnetic fields are generated by convection in the metallic cores of planets, the movement of electrically conducting material in the interior that generates currents and therefore magnetic fields. For a tidally locked planet, rotation is very slow relative to a star, which might reduce the efficiency of magnetic field generation. But models are inconclusive. Some suggest that thermal convection can maintain significant magnetic fields even in slow rotation. The definitive answer will require direct observations of the magnetic fields of these planets, which are beyond current capabilities but might be achievable with future instruments. Tidally locked worlds are probably the most abundant habitable planets in the galaxy. Red dwarfs are the most common stars, and the planets in their habitable zones, which orbit close and lock quickly, are the most numerous habitability candidates in the catalog. If life can adapt to the eternal sunrise of the terminator, to the perpetual wind blowing from day to night, to the absence of the cycle that has regulated terrestrial biology for 4 billion years, then life could be very common in the galaxy. If it cannot, if that cycle is essential, then the galaxy could be far lonelier than the numbers suggest. The answer, which we don't have yet, will fundamentally determine our understanding of how alone or accompanied we are in the cosmos. There is also a subtler and stranger implication of the tidal locking question for the arc of life's history on such worlds. On Earth, the day-night cycle shaped the evolution of life in ways we are only beginning to understand. The circadian clock, the internal biological timer that virtually all life on Earth carries, is so deeply embedded in cellular biology that it appears to have evolved very early, possibly in the first cells. Plants orient their growth by the daily light cycle. Animals navigate by the position of the sun. Human sleep, metabolism, immune function, and mood are all controlled by circadian rhythms tied to the 24-hour day. On a tidally locked world, there is no 24-hour day. The only cycle is the orbital period, which for a planet in the habitable zone of a red dwarf might be 5 to 15 Earth days. Any life that arose there would have to work with that very different clock, or evolve without a clock at all, driven instead by spatial position relative to the terminator rather than by temporal cycles. The question of tidal locking is inseparable from the broader question of whether life in the galaxy is mostly in the neighborhoods of red dwarfs or mostly in the neighborhoods of sun-like stars. Red dwarfs are by far the most common, and they live for tens to hundreds of billions of years, far longer than the Sun's 10 billion-year lifetime. A planet orbiting a red dwarf has had more time, potentially much more time, for life to arise and evolve than Earth has had. But the challenges of tidal locking, stellar flares, and ultraviolet irradiation are real. Whether those challenges are surmountable by life, or whether they are absolute barriers, is the question that will shape our understanding of biology and the cosmos for decades to come. The horizon that never changes. The star that never moves. The wind that always blows in the same direction. It could be the landscape of a world where life found its way, adapting patiently to an eternity of dawn. Or it could be the landscape of a sterile and silent world, where the winds blow over bare rock with nothing to feel them. We don't know yet. But the question is the most important one astronomy can ask. There is a moment in the original Star Wars film where young Luke Skywalker stands in the desert of Tatooine watching the horizon as two suns set simultaneously, one after the other, in shades of orange and red. It is one of the most iconic images in science fiction, and for decades it was considered purely imaginary, a fantastical detail of an invented universe. That was a reasonable conclusion at the time the film was made. No real planetary system with two stars and a planet had been confirmed. The orbital dynamics of binary systems were so complex that many astronomers doubted they could harbor stable planets. And then the Kepler telescope began looking at the sky, and it turned out the galaxy was full of Tatooines. Planets that orbit around two stars are called circumbinary. The prefix circum indicates they orbit around the complete stellar pair, rather than orbiting a single star with the other at a great distance. In a circumbinary system, the two stars orbit each other at relatively small separations, orbital periods of days to weeks, and the planet orbits around the center of mass of the complete pair at a greater distance. The orbital dynamics of these systems are complex. The planet's orbit is constantly perturbed by the gravitational influence of both stars, and not all orbits are stable. There is a minimum orbital radius, called the critical radius, inside which no stable orbit for a planet is possible, because the gravitational perturbations from the stellar pair would destabilize it over time. Circumbinary planets are found at or beyond this critical radius. The first confirmed circumbinary planet was Kepler 16b, announced in September of 2011. It orbits a pair of stars, one roughly 2/3 the mass of the Sun, one roughly a fifth of the Sun's mass, at a distance of about half an astronomical unit, completing one orbit in 229 days. Its radius is approximately 8/10 of Jupiter's radius and its mass is roughly 1/3 of Jupiter's. It is a cold, Saturn-like planet, too cold for liquid water, with temperatures estimated around -100 degrees Celsius. But the key fact about Kepler 16b was not its temperature or its composition. It was simply that it existed at all. A planet orbiting two stars. A real Tatooine in the galaxy, detected by a spacecraft built by humans, 42 light-years from Earth. The discovery of Kepler-16b was followed rapidly by the discovery of more circumlunar planets in the Kepler data: Kepler-34b, Kepler-35b, Kepler-38b, Kepler-47b and c, and many more. The catalog of confirmed circumlunar planets now numbers in the dozens, with many more candidates awaiting confirmation. The statistical abundance of circumlunar planets in the Kepler data suggests that they are not rare, that the formation of planets in binary star systems is not significantly suppressed compared to formation around single stars. This was itself a surprise. Many had expected that the complex and time-varying gravitational environment of a binary star system would prevent stable protoplanetary disks from forming, or would disrupt planet formation before it could proceed. Instead, the observations show that nature finds a way. What would life look like on a circumlunar planet? The sky would be its most immediate and striking difference from Earth. On any given day, one of the two suns might be larger and brighter in the sky, if the two stars are of unequal size, as they usually are, while the other appears as a smaller, perhaps yellower or redder point of light. The relative positions of the two suns in the sky would change throughout the planet's year as both the planets orbit around the stellar pair and the stellar pairs orbit around each other, produce a complex, non-repeating pattern of apparent positions. There would be no simple concept of a solar day. The two suns would rise and set at different times, and on some days both would be above the horizon simultaneously for hours, creating a bright double-lit afternoon, while on other days, perhaps during mutual eclipse events of the two stars, the sky might suddenly dim as one star passes in front of the other. The seasons on a circumlunar planet would also be more complex than those on Earth. Earth's seasons arise from the tilt of Earth's rotational axis relative to the plane of its orbit. The same hemisphere faces the Sun more directly in summer and less so in winter. On a circumlunar planet, the variable distance to the center of mass of the stellar pair as the planet orbits, combined with the changing configuration of the two stars, would produce seasonal variations in total stellar irradiation that follow patterns more complex than Earth's simple sinusoidal annual cycle. For some orbital configurations, the variation in total solar energy received over the planet's year could be quite large, potentially driving dramatic seasonal climate changes. One of the most fascinating circumlunar systems discovered by Kepler is Kepler-47, which hosts not one but two confirmed planets orbiting the binary star pair, and possibly a third. The inner planet, Kepler-47b, is about 3 Earth radii in size and orbits the stellar pair in 49 days. The outer planet, Kepler-47c, has a radius of 4.5 Earth radii and orbits in 303 days, placing it in the habitable zone of the system. It is the first planet in the habitable zone of a binary star system ever confirmed. It is probably a mini-Neptune, too gassy for a rocky surface, but it demonstrated that habitable zone orbits in binary systems were not only theoretically possible but actually found in the Kepler data. The formation of circumlunar planets presents theoretical challenges that are still not fully resolved. The standard core accretion model of planet formation, in which a rocky core grows by accumulating solid material from the protoplanetary disk, runs into difficulties close to the critical radius of a binary system, where the gravitational perturbations from the two stars stir up the disk material to high velocities and make gentle collisions, the collisions needed for accretion, very difficult. Instead of building up, planetesimals near the critical radius tend to collide at high enough speeds to break apart rather than stick together. This suggests that circumlunar planets don't form close to the critical radius, they form farther out, where the perturbations are weaker, and then migrate inward to their current observed locations. It is a variation on the same migration theme that explains hot Jupiters, applied to a more gravitationally complex environment. TESS, the successor to Kepler, has continued to find circumlunar planets in the solar neighborhood, closer and brighter systems than those found by Kepler, making them more accessible for detailed follow-up observations. TIC 172900988b, announced in 2021, is a circumlunar planet slightly larger than Jupiter discovered by TESS in a relatively close system, and was the first circumlunar planet found by TESS to be confirmed through multiple observing methods. The discovery demonstrated that TESS's wider sky coverage and focus on brighter stars would be able to build on Kepler's census of binary star worlds with systems accessible to full atmospheric characterization. There is something poetically appropriate about the double sunset. The universe doesn't simplify things for the beings who might live in it. It offers multiple suns, complex seasons, skies that never repeat their pattern. The galaxy contains perhaps billions of circumlunar planets. Some of them are probably inhabitable zones. Some of them might have complex weather, complex skies, complex enough environments to have driven, if life arose there, the evolution of complex living things adapted to a sky with two suns, days that don't follow simple patterns, seasons that never quite repeat. There is something poetically appropriate about the double sunset. The universe doesn't simplify things for the beings who might live in it. It offers multiple suns, complex seasons, skies that never repeat their pattern. The galaxy contains perhaps billions of circumlunar planets. Some of them are probably inhabitable zones. Some of them might have complex weather, complex skies, complex enough environments to have driven, if life arose there, the evolution of complex living things adapted to a sky with two suns, days that don't follow simple patterns, seasons that never quite repeat. The complexity of a circumlunar sky raises a question that scientists and science writers rarely ask. What would the mythology of a circumlunar civilization look like? The most ancient human myths are tied to the sky, to the rising and setting of a single sun, to the phases of a single moon, to the consistent patterns that made our ancestors' sky a reliable map and calendar. On a circumlunar world, the sky would never be a simple map. The two suns would trace different paths. Their positions relative to each other would shift over days and years. Eclipses of one star by the other would darken the sky unpredictably. The patterns would be there, but they would be more complex, requiring more sophisticated mathematics to decode. Perhaps a circumlunar civilization would be, by necessity, better astronomers than we were for most of our history, forced from the beginning to track two suns instead of one. And on some of them, perhaps, somewhere in the galaxy, something stands at the edge of a landscape we cannot imagine, and watches two suns descend toward a horizon that is only that world's horizon, with colors that have no name in any human language. And the universe, as it always does, continues its ancient work in perfect silence. We have visited worlds of liquid iron rain, glass storms, lava oceans, diamonds, perpetual twilight, and double sunsets. But the catalog of exoplanets has extremes that reach beyond all of these, worlds where the temperatures, pressures, densities, orbital speeds, and atmospheric compositions push against the outer limits of what the known laws of physics permit. Tonight, as we begin the slow descent towards sleep, we visit a handful of those boundary worlds. Not for their danger, they are all impossibly far away, but for what they tell us about the range of outcomes that a universe with these particular physical laws can produce. At the extreme of orbital speed, consider WASP-19b, a hot Jupiter that completes one orbit around its star in just 18 hours and 52 minutes. It is the hot Jupiter with the shortest known orbital period, so close to its star that the tidal forces acting on it are immense, and models predict the planet is slowly spiraling inward. Observations over the past decade have detected a slow decrease in its orbital period, a few milliseconds per year, consistent with the planet losing orbital energy to tidal dissipation. WASP-19b is slowly falling into its star. The process will take millions of years, but it is real and it is measurable. We are watching, in slow motion, the death of a planet. Its final fate is absorption by its host star, or tidal disruption before it even reaches the stellar surface. The tidal forces could rip the planet apart while it's still in orbit, spreading its material into a disk around the star, a temporary planetary ring, before it accretes onto the star over thousands of years. At the extreme of temperature, P7b reaches dayside temperatures of approximately 2,700 degrees Celsius, hot enough to vaporize most minerals and rocks, hot enough for aluminum oxide clouds to form in the upper atmosphere. Those aluminum oxide clouds, corundum, the same mineral that forms rubies and sapphires when trace amounts of chromium or iron are incorporated into it, are the most exotic clouds yet inferred in any planetary atmosphere. The gem clouds of P7b exist at the boundary between the day and night hemispheres, condensing on the cooler night side terminator and evaporating when they are carried into the blazing day side by the winds. They are jewel clouds in a supersonic wind on a world where the rock itself evaporates. At the extreme of darkness, Trace 2b absorbs more than 99% of all the light that falls on it, making it darker than coal, darker than any planet or moon in our solar system. The reason for this extreme darkness is not fully understood. The suspected explanation involves a combination of sodium, potassium, and gaseous titanium oxide in the atmosphere that together absorb across the full visible spectrum with extraordinary efficiency, leaving almost nothing to be reflected. Despite being a hot Jupiter extremely close to its star, Trace 2b reflects less than 1% of the light it receives. If you could see it from the side, it would appear as a perfect black sphere against the brightness of its star, a planet-sized void in the light. At the extreme of mass among confirmed planets, P2b has approximately 9 Jupiter masses, close to the theoretical upper mass limit for objects that form in planetary disks rather than by direct gravitational collapse like brown dwarfs and stars. It orbits its star in a highly eccentric orbit, swinging from close approaches that take it inside the orbit of Mercury's equivalent to distant aphelion, then back again, over 5.5 days. During its closest approach to the star, the planet receives 30 times more stellar radiation than at its farthest point, creating wildly variable atmospheric conditions that cycle from extreme heat to relative cold over the course of a single orbital period. The atmospheric pressure waves and temperature changes driven by this orbital variation have been detected through infrared phase curves, making HAP-P2b one of the most dynamic planetary atmospheres ever studied. Among the smallest confirmed exoplanets is Kepler-37b, with a radius of just 37% of Earth's radius, smaller than Mercury. That measurement was itself a triumph of precision photometry, detecting the transit of a Mercury-sized body across a distant star with a telescope that measured brightness changes of parts per million. Kepler-37b is one of a system of at least 3 planets, of which the other 2 are larger. It orbits so close to its star that any atmosphere it might have had was long since stripped away by the stellar radiation. It is almost certainly a bare rock, without air, without water, baking in the heat of a sun-like star at temperatures exceeding 400 degrees Celsius. Among the lowest density confirmed planets is Kepler-51b, with a density of approximately 1/20th of a gram per cubic centimeter. Water has a density of 1 gram per cubic centimeter. Kepler-51b is 20 times less dense than water, roughly the density of expanded polystyrene foam. It is a planet that would float, dramatically and improbably, in a large enough ocean. Its extraordinary puffiness arises from its extreme atmospheric inflation. It is a sub-Saturn with a hydrogen and helium envelope so massively swollen by its star's heat that the planet's radius is far larger than any interior structure model would predict for its mass alone. It is, in a sense, a planet that is mostly nothing, mostly empty space, a vast extended envelope of nearly vanishing density wrapped around a relatively small core. At the extreme of atmospheric chemistry, the planet K2-18b occupies a category all its own. With a radius of 2.6 Earth radii and a mass of about 8.6 Earth masses, it sits squarely in the mini-Neptune range, but it is in the habitable zone of its red dwarf host star. Webb observations published in 2023 detected carbon dioxide, methane, and, in a detection that generated enormous excitement and controversy, dimethyl sulfide, or DMS, in its atmosphere. On Earth, DMS is produced almost exclusively by biological processes, by marine phytoplankton. If the DMS detection is confirmed, it could be the first tentative biosignature in an exoplanet atmosphere. Most scientists are appropriately cautious. DMS can potentially be produced by abiotic chemistry as well. The detection is at the edge of statistical significance, and K2-18b is likely not a rocky world but a Hycean world, a proposed class of ocean worlds with hydrogen-rich atmospheres that may or may not be habitable. But the possibility, however uncertain, is real, and K2-18b will be observed repeatedly with Webb and with future telescopes to either confirm or rule out the signal. The extreme reaches of the exoplanet catalog are not just a collection of curiosities. They are the stress tests of planetary physics, the cases where the standard models of planetary formation, atmospheric dynamics, and interior structure are pushed beyond their usual domain and forced to either generalize or fail. Every extreme planet teaches us something about the range of outcomes available in a universe with these particular constants, these particular forces, these particular initial conditions. And collectively, they draw a picture of a cosmos that is not gentle with its creations, not designed for comfort or stability, but that produces from the same physical laws a staggering and humbling variety of outcomes. There is something unexpectedly comforting about that variety. The universe is not monotonous. It doesn't repeat the same solution endlessly. It explores. It finds the edge cases, the exceptions, the configurations that theory would classify as improbable. A planet darker than coal. A planet less dense than foam. A world where jewelry condenses from the air. A world slowly falling into its sun. These are not failures of the universe's design. There is no design. They are the natural consequence of physical laws applied without restriction to all available initial conditions, producing a distribution of outcomes that spans the entire range of what those laws allow. We, on our unremarkable rocky world in a quiet corner of an average galaxy, are somewhere in the middle of that distribution. Neither the most extreme nor the most ordinary. Just one outcome among billions. Somewhere out there, at distances that light takes decades to centuries to cross, a planet is raining iron in the dark. Another is bathed in the light of two suns. Another is falling slowly into its star. Another is so dark it drinks in light and gives nothing back. Another may host something living in its deep ocean. They are all real. They are all there, right now, while you lie here in the quiet. The universe is vastly, incomprehensibly strange. And we have barely begun to see it. Let that be the last thought before sleep. Not worry. Not the noise of the day. Just the strangeness. The iron rain. The double sunsets. The darkness that drinks light. The ocean that might not be empty. Rest now. The strange worlds will keep being strange, whether or not you are awake to wonder at them. There is a question that sits at the heart of everything we have explored in this series, a question that makes the iron rain and the glass storms and the lava oceans and the double sunsets more than just beautiful curiosities. A question that transforms the catalog of 5,000 worlds from an inventory of wonders into something with urgency, with stakes, with the weight of the deepest uncertainty humans have ever faced. The question is simple to state. It is perhaps the hardest question our species has ever asked. And it is this: are we alone? Not in the philosophical sense, not whether the universe is indifferent to human existence, not whether there is meaning in a cosmos of billions of galaxies. In the most literal, empirical sense. Is there, somewhere among the hundreds of billions of planets in the Milky Way, another world where chemistry has organized itself into self-replicating structures that extract energy from their environment, respond to their surroundings, and grow more complex over time? Is there life? Not intelligence necessarily. Not civilization. Just life, the basic, astonishing fact of biology existing somewhere other than the thin film of the surface and oceans of Earth. The honest answer, as of the moment these words are written, is that we do not know. We have found no confirmed evidence of life anywhere other than Earth. Every candidate signal, every intriguing molecule detected in a distant atmosphere, every anomalous brightness variation, every puzzling chemical abundance, has either been explained by abiotic processes, remains ambiguous pending further observations, or has quietly disappeared on reanalysis. The universe has not yet sent us an unambiguous signal. But the search is young, the instruments are new, and the methods are improving faster than at any point in the history of science. The scientific strategy for detecting life at astronomical distances rests on a concept called the biosignature. A biosignature is any observable property, a chemical compound, a gas, a spectral feature, a physical characteristic, that would be difficult or impossible to produce by non-biological processes alone, and whose presence in the atmosphere or on the surface of a planet would therefore constitute evidence for the presence of life. The gold standard biosignature for Earth-like life is the combination of oxygen and methane in the same atmosphere. Oxygen, in the form of molecular O2, is produced on Earth almost entirely by photosynthesis. Methane is produced on Earth largely by biological metabolism, by microbes in wetlands, in the guts of animals, in the ocean sediments. In the presence of oxygen, methane reacts chemically and is destroyed in a matter of decades. The fact that both gases are simultaneously present in Earth's atmosphere in the concentrations they are is a profound chemical disequilibrium, one that can only be maintained against the tendency of chemistry to reach equilibrium if there is a constant biological source replenishing both. An observer with a sufficiently sensitive spectrograph, looking at Earth from another star, could detect that disequilibrium and infer life. The detection of biosignatures in exoplanet atmospheres is the central scientific goal of the next generation of telescopes. The James Webb Space Telescope has already taken the first steps in this direction. In 2023, Webb observations of K2-18b, a sub-Neptune in the habitable zone of a red dwarf, detected carbon dioxide, methane, and a tentative signal of dimethyl sulfide, or DMS. On Earth, DMS is produced almost exclusively by marine phytoplankton. It is a metabolic byproduct of ocean microbes that has no known efficient abiotic production pathway in rocky planet environments. If the DMS detection is confirmed with additional observations, it would be the first candidate biosignature in an exoplanet atmosphere. Most scientists are appropriately cautious. The detection is at the edge of statistical significance. DMS has been proposed to form abiotically under certain conditions, and K2-18b may be a Hycean world, a planet with a hydrogen-rich atmosphere over a liquid water ocean, whose habitability remains uncertain. But the signal is real enough that it demands follow-up, and that follow-up is underway. The technical challenge of detecting biosignatures is staggering. For a planet orbiting a Sun-like star, the planet's signal during a transit is roughly 10,000 times fainter than the star's signal. Detecting the presence of trace gases like oxygen or ozone at concentrations of tens of parts per million in that already faint signal requires a precision that pushes against the fundamental limits of current photon collection technology. The signal of Earth's oxygen in transit, as seen from a hypothetical observer at a nearby star, would be detectable with a telescope of roughly 30-meter aperture taking multiple transits, achievable in principle with the next generation of extremely large telescopes being built now, but only for the very nearest stars. For most of the TRAPPIST-1 planets, which are among the best current targets, detecting oxygen at Earth-like concentrations with Webb would require more transits than occur in a human lifetime. The goal is ambitious, but the instruments are improving, the targets are being identified, and the first serious attempts are already underway. Beyond the oxygen-methane combination, astrobiologists have proposed a range of other potential biosignatures. Nitrous oxide, or laughing gas, is produced on Earth primarily by microbial activity in soils and oceans and accumulates to detectable levels when biological productivity is high. Phosphine, a molecule of one phosphorus atom bonded to 3 hydrogens, has no known efficient abiotic production pathway on rocky planets and would be a strong biosignature if detected. The the famous controversy over the claimed detection of phosphine in Venus's atmosphere in 2020, which generated enormous public excitement before subsequent analyses cast serious doubt on it, illustrated both the promise and the difficulty of biosignature science. The signal was eventually attributed to calibration artifacts in the telescope data, not to phosphine. But the episode also showed that the scientific community has the tools and the critical rigor to evaluate such claims carefully, even under enormous public pressure. The concept of a biosignature extends beyond atmospheric chemistry. Surface biosignatures include the so-called vegetation red edge. The sharp increase in reflectance of plant leaves just beyond the red visible wavelengths, produced by chlorophyll, which reflects near-infrared light strongly and absorbs visible red light. Earth has a planet-wide vegetation red edge signature that a sufficiently sensitive telescope could detect from nearby stars. An analogous signature might exist on a planet where photosynthesis uses a different pigment, and since different stars emit light at different wavelengths, life on planets orbiting red dwarfs might evolve photosynthesis pigments tuned to red or near-infrared light, producing surface color signatures very different from Earth's green-dominated vegetation. The signature of life on another world might look nothing like life on Earth, and searching for it requires thinking beyond the specific chemical fingerprints of Earth biology. This last point opens one of the deepest and most difficult questions in astrobiology: how universal is life? Earth life is built on a specific set of molecules: DNA, RNA, proteins, lipids, carbohydrates, organized around the chemistry of carbon, water, and a handful of other elements. That chemistry is extraordinarily effective, and there are good physical and chemical reasons to expect that carbon-based life in liquid water would be favored wherever the conditions allow. But is it the only possibility? Could there be life based on silicon chemistry? On ammonia as a solvent instead of water? On exotic chemistries and environments we haven't imagined? Most astrobiologists are cautious about claiming that carbon-water life is the only possibility, while acknowledging that it is the only form of life we know, and therefore the most reasonable starting point for the search. If life elsewhere uses fundamentally different chemistry, our current biosignature search strategies might miss it entirely. It is a humbling uncertainty to carry. The search for life is also, inevitably, a search for planets that resemble Earth in some ways, not because Earth is the template for all possible life, but because it is the only data point we have. The criteria for an Earth-like planet are roughly rocky composition, mass between 1/2 and 3 Earth masses, surface temperature allowing liquid water, atmosphere with moderate greenhouse effect, presence of the essential biochemical elements. The number of planets meeting all those criteria, with current observational constraints, is small but not zero. Proxima Centauri b, the nearest known exoplanet at just 4 light-years, is in the habitable zone of its red dwarf host, but is probably tidally locked, and the star is highly active with frequent flares. LHS 1140b at 49 light-years is a more promising candidate, with a potentially dense atmosphere suggested by Webb observations. TRAPPIST-1e remains one of the most carefully studied targets for habitability. None of these planets has had its atmosphere characterized in enough detail to rule in or out the presence of life. But each new observation narrows the range of possibilities. There is also the question of time. Life on Earth took several 100 million years to appear after the planet's surface cooled enough for liquid water to exist, a geologically short time, suggesting that life may arise readily whenever conditions are right. But complex, multicellular life took another 3 billion years. And intelligence, as far as we know, has existed for at most a few million years out of Earth's 4.5 billion year history. The cosmic window for detecting technological life, life that modifies its environment in ways we could detect from a distance, is very narrow compared to the window for detecting simple microbial life. If we find biosignatures in an exoplanet atmosphere in the coming decades, they will almost certainly be the signatures of microbial life rather than of anything we would recognize as complex or intelligent. That would still be the most transformative discovery in the history of science. The confirmation that life is not unique to Earth, that biology is a feature of the universe, not an accident of one particular planet, would change everything. Every philosophy, every religion, every science, every story we tell about who we are and why we are here. We don't know yet. The answer is out there, in the spectrum of some distant star, encoded in the molecular composition of an atmosphere we haven't observed with enough precision. The instruments to read that spectrum are being built. The targets are being identified. The methods are being refined. And somewhere in the galaxy, in this very moment, if life exists on another world, it is going about its business in complete ignorance of the fact that a species 4 billion years into its own biological history, on a small rocky planet in a quiet corner of an ordinary galaxy, has learned to read the light of stars well enough to ask the question, and is getting close to being able to hear the answer. The temporal dimension of the search adds a layer of complexity that is rarely discussed outside the scientific literature. When we detect a biosignature in an exoplanet's atmosphere, we are seeing that atmosphere as it was when the light left the planet, which for nearby stars means years to decades ago, and for more distant systems means centuries or millennia. If the biosignature reflects a biosphere that arose and then collapsed in the intervening time, we would have no way to know. We would be reading the fossil record of a biosphere, not a live report. The light arriving at our telescopes tonight from Proxima Centauri departed 4 years ago. The light from the TRAPPIST-1 system departed 40 years ago. Every exoplanet observation is, in this sense, archaeology. We are asking not is there life there now, but was there life there then? The distinction matters less for long-lived biospheres like Earth's, where the biosignature has been essentially constant for nearly 2 billion years, but it matters for any biosphere that might be younger or more transient. There is also a more radical possibility that astrobiology has begun to take seriously, that life, wherever it exists, might be so different from Earth life that our entire search strategy would fail to detect it. The molecules we search for, oxygen, methane, water, nitrous oxide, dimethyl sulfide, are the metabolic byproducts of Earth's specific biochemical machinery. A biology based on different chemistry, silicon compounds, ammonia-based reactions in cold environments, exotic polymers in conditions we haven't yet imagined, would produce different spectral signatures, different surface colors, different atmospheric fingerprints. The possibility that life could be genuinely invisible to the detection strategies we have built is one of the deepest uncertainties in astrobiology. It is why some researchers argue that alongside targeted searches for specific biosignatures, we should also conduct broad-spectrum surveys looking for any chemical disequilibrium, any atmospheric composition that cannot be explained by known abiotic processes, regardless of whether the specific molecules match Earth's biological fingerprints. And yet, despite all these uncertainties, the search is real, the instruments are extraordinary, and the targets are known. The TRAPPIST-1 planets, LHS 1140b, Proxima Centauri b, and dozens of other rocky worlds in or near the habitable zones of nearby stars. These are not hypothetical. They exist. Their atmospheres are being observed right now. The data is being analyzed. The papers are being written. The conversation between humanity and the universe, conducted in the language of light and wavelength and molecular absorption, is ongoing and accelerating. Rest with that. The search continues, whether or not you are awake. The light from distant atmospheres is arriving at our telescopes right now, carrying its secrets, waiting for the right instrument and the right analysis to reveal them. We have traveled a long way tonight. From the first exoplanet discoveries of the 1990s to iron rain and glass storms, from lava oceans and diamond interiors to rogue planets in the dark, from ocean worlds to tidally locked twilight zones, from binary sunsets to the question of whether anywhere else in the galaxy something looks up at a night sky and wonders. We have crossed distances that light takes years or centuries to bridge, visiting worlds that have existed for billions of years and will exist for billions more, entirely indifferent to our attention, entirely unaware of the small blue planet from which their light was studied. And through all of it, the science has been moving forward, the instruments improving, the questions sharpening. Tonight, as we move towards sleep, we take one final look at where the search is going, at the telescopes being built, the missions being planned, the discoveries being prepared for us by scientists who are working right now, in laboratories and at observatories around the world and in space, asking the next questions. The James Webb Space Telescope is the anchor of the present era. Launched on Christmas Day of 2021 and reaching its operational orbit at the second Lagrange point, a gravitationally stable position 1 million miles from Earth, Webb has already transformed exoplanet science in its first few years of operation. Its 6.5-meter gold-coated mirror, segmented into 18 hexagonal panels that unfolded in space like a mechanical flower, collects infrared light with a sensitivity that previous instruments couldn't approach. Its instruments, NIRCam, NIRSpec, MIRI, and FGS/NIRIS, cover wavelengths from the near-infrared to the mid-infrared, the range in which the molecular fingerprints of water, carbon dioxide, methane, sulfur dioxide, and dozens of other atmospheric constituents are most pronounced. In its first years, Webb has produced atmospheric spectra of precision that previously required 10 or 20 transits to achieve from a single observation. It has detected carbon dioxide, water, sulfur dioxide, methane, and carbon monoxide in exoplanet atmospheres with a clarity that stunned even those who designed it. It has built the first detailed phase curves and temperature maps of rocky planets in habitable zones. And it is barely getting started. Webb is designed to operate for at least 20 years, and the science it will produce over the rest of its lifetime will dwarf what it has already done. On the ground, the new generation of extremely large telescopes is rising. The European Extremely Large Telescope, the ELT, is under construction on Cerro Armazones in the Atacama Desert of Chile, with a primary mirror 39 meters in diameter, larger than any telescope that has ever existed. It will begin scientific operations around 2028. The 30-meter telescope, planned for Mauna Kea in Hawaii, and the Giant Magellan Telescope, under construction at Las Campanas Observatory in Chile, complete the trio of next-generation ground-based giants. These telescopes will have the angular resolution and the light-collecting power to perform high-resolution spectroscopy of the atmospheres of nearby exoplanets, including, for the first time, planets orbiting the nearest stars, with a precision that makes the detection of Earth-like atmospheric compositions theoretically feasible for the nearest targets. The ELT's METIS instrument, designed for mid-infrared imaging and spectroscopy, and its Andes spectrograph, designed for ultra-high-resolution spectroscopy in the visible and near-infrared, are specifically tailored for exoplanet atmosphere characterization and biosignature searches. In space, the European Space Agency's Plato mission, Planetary Transits and Oscillations of Stars, is planned for launch in the early 2030s. Plato will monitor more than 200,000 bright, nearby stars simultaneously, searching for transits of Earth-sized planets in orbits of 1 to 2 years around Sun-like stars. Current transit surveys like TESS are most sensitive to short-period planets, those with orbits of days to weeks, because more transits occur in the observation window and the transit probability for close-in planets is higher. Plato will extend the sensitivity to the period range where truly Earth-like planets, rocky planets with year-long orbits in the habitable zones of Sun-like stars, are found. The planets Plato discovers will be around nearby, bright stars, making them accessible for atmospheric characterization with the ELT in Webb. Plato is expected to discover dozens of Earth-like planet candidates, and to identify the best targets for the most ambitious search of all. That most ambitious search is embodied in the concept of NASA's Habitable Worlds Observatory, or HWO. The HWO concept, studied extensively in the last decadal survey of astronomy, which set it as the top priority for the next large NASA space telescope, envisions a space telescope of 6 to 8 meters aperture, equipped with advanced coronagraph technology to block the light of nearby stars and reveal the reflected light of their planets directly. Direct imaging is the only technique that allows simultaneous measurement of the planet's reflected spectrum across a broad wavelength range without depending on the alignment of the planet's orbit with our line of sight. A planet doesn't need to transit its star to be imaged directly. The HWO could observe dozens of nearby Sun-like stars and detect reflected light from their Earth-sized planets in the habitable zone, and from those spectra, search for the simultaneous presence of water vapor, oxygen, and ozone, or other biosignature combinations, with enough sensitivity to make a detection or a meaningful non-detection within a few years of operation. If funded and constructed on the timeline being discussed, HWO could be operational sometime in the 2040s or early 2050s. Within the lifetime of children alive today. Beyond individual telescope missions, the landscape of exoplanet science is being transformed by the sheer scale of data from sky surveys. The Vera C. Rubin Observatory, now in operation, will produce petabytes of astronomical data over its 10-year legacy survey of space and time, including photometric measurements of billions of objects that will enable new statistical analyses of planetary populations, microlensing detections of rogue planets, and serendipitous discoveries that no one has yet thought to plan for. The Gaia mission of the European Space Agency, which has measured the precise positions and motions of nearly 2 billion stars, has and will continue to reveal the astrometric signatures of giant planets orbiting nearby stars. planets detected not by their transit or their spectral effect on the star but by the tiny gravitational wobble they induce in the star's position on the sky. Gaia's final data releases will include a catalog of hundreds or thousands of astrometrically detected planets, providing a statistically complete view of the giant planet population around nearby stars that complements the transit and radial velocity catalogs beautifully. There are also more speculative but scientifically serious proposals on the longer-term horizon. The star shade concept, a large, precisely shaped screen deployed in space tens of thousands of kilometers from a space telescope, blocking starlight with exquisite precision to allow direct imaging of exoplanets, has been studied in detail by NASA as a potential enhancement to the HWO. The concept works because starlight travels in parallel rays from a distant star, and a precisely shaped occulter can diffract those rays away from the telescope aperture, suppressing the stellar light by 10 orders of magnitude while leaving the planet's reflected light largely unaffected. Laboratory demonstrations of the required optical precision have already been achieved. The engineering challenge is formidable, but not more formidable than building the James Webb Telescope itself was a generation ago. Looking further into the future, mission concepts for small interstellar probes have been studied seriously under the Breakthrough Starshot Initiative, which proposes using ground-based laser arrays to accelerate gram-scale spacecraft to 20% of the speed of light. At that velocity, a probe could reach the Proxima Centauri system in approximately 20 years. The cameras and sensors such a probe would carry could return images and atmospheric data from Proxima Centauri, being the first ever direct reconnaissance of another stellar system. The engineering challenges are enormous, keeping the laser focused on a fast-moving target, protecting the probe from interstellar dust at relativistic speeds, transmitting data back over 4 light-years with gram-scale electronics, but none of them violates any known physical law. This mission could, in principle, be achieved within the 21st century. The arc of the science is clear, even if the timeline is uncertain, from detection to characterization, from mass and radius to atmospheric composition, from atmospheric composition to biosignatures, from biosignatures to, perhaps, the answer to the question that has driven all of this. Each step requires better instruments, more observation time, more theoretical understanding, more patience. But each step is taken. Each instrument is built. Each observation is made. And the question, which was purely philosophical for all of human history before 1992, has become empirical. It is now the kind of question that data can answer. That transition, from philosophical to empirical, is one of the most important moments in the intellectual history of our species. We began this series with a question that no human could have asked 30 years ago. Tonight, after traveling across 14 strange worlds, we end with the same question, now better informed, more precisely posed, backed by the most powerful astronomical instruments ever built. The question hasn't been answered. But the tools to answer it exist, or are being built. The targets are identified. The methods are refined. The search is real, it is ongoing, and it is the most important scientific enterprise our species has ever undertaken. The strange worlds we visited, WASP 76b with its iron rain, HD 189733b with its glass storms, 55 Cancri E with its lava ocean and possible diamond heart, Kepler 7b with its western clouds glowing in the dark, the rogue planets in their eternal solitary journeys, the ocean worlds silent beneath miles of liquid, the tidally locked worlds in their perpetual twilight, the binary systems with their impossible double sunsets, all of them were part of the same catalog. The same inventory of what the universe built with one set of physical laws, applied everywhere, without preference or intention, producing everything from iron rain to the possibility of life. We are part of that catalog. Earth is one of the strange worlds. To a hypothetical astronomer orbiting Tau Ceti or Epsilon Eridani, our Sun is an unremarkable G-type star in a quiet region of the galaxy, and Earth, if they could detect it, would be a small rocky planet with an anomalous oxygen-methane atmosphere and an unusual amount of liquid water on its surface, maintained in a state of profound chemical disequilibrium by something that keeps replenishing both gases simultaneously. They might wonder what we wonder. They might ask the same question we ask when we look up. Sleep now. The search continues in the dark. The light from distant worlds is arriving at our telescopes right now. The instruments are watching. The data is accumulating. And somewhere, in the spectrum of some unremarkable star in a direction we haven't yet looked carefully enough, the answer might already be encoded, waiting for the right night, the right instrument, the right human being to notice. The universe is patient. It has been waiting billions of years for someone to ask. It can wait a little longer for the answer. Good night.